Hi, good evening, everyone.
Good evening, sir.
Okay, so I think today is week 5 and 6 solve the session, right?
Sir, your voice is low.
Okay, just a minute. Is it okay now? Is it okay?
Yes, sir.
Okay. So I think we have week 5 and 6 revision session today for quiz 2, right? I hope all of you have gone through this. Mostly three topics are there. One is linear regression. Then the two variants of it. One is ridge regression and the lasso regression, right? Is that fine? So we'll try.
Yes, sir.
So I'll try to cover those topics which are very important to like. Uh, it is important for your quiz to all right. Fine. So it's like we are not going into all the details which are there. We'll just stick to the those concepts which are very much required for your quiz too, right?
Okay, sir. Sir, is the mock release for Amal?
I think mock is released, right, already. Uh, Not sure about it, but I think it is released because we have sent an email. I remember that mock has already been there. Uh, what do you want from me related to the mock?
No, sir. Actually, yesterday it was not released.
Mock was released yesterday. You're saying
No, sir. Not released yesterday.
not released. I
Yes, sir. Mock is not released yet.
Okay, okay. I have seen the message going. Okay, let me check. Okay.
No, sir. It's not there.
Okay, okay. I'll check. I'll check. Okay, if it is not released, then it will get released. Okay. Okay, fine. Okay. So okay. Anyway, the mock will get released. That is a different discussion. For now, we'll start on what are the topics which are important with respect to linear regression. So supervised learning. Linear regression is one of the types of supervised learning, and why it is called supervised learning? Because it has this kind of data set, right? Okay, my screen is visible, right?
Yes, sir.
Yeah. So the data set,
Yes, sir. Visible.
yeah. So the data set for any supervised learning task will look like what? It will be looking like this: x1, x2 till let's say xn. So there are n number of examples, uh, right? And uh, whatever the uh, whatever the features are there, their corresponding labels are given to us, right? Or this is any kind of supervised learning task will look like this, right? Each of xi in this case will be in uh, it is in d-dimensional. N is number of examples which are there in during your training. So this data set is available for us for the training, right? I hope all of you understand that part. Training is what we are training to. Okay, so we are learning any mathematical model, right? Out of it, and that mathematical model will be uh, uh, let's say it can be any sort of you're saying that in this case linear regression you have that y equal to mx plus c. That kind of mathematical model we'll be learning here. So each of xi in this case will be in d dimensions, and the corresponding labels, if they are uh, real numbers, then that kind of problem is called as what? Regression problem, right? You're trying. So during your training, each of these labels or yi's, right? They are actually in they are the continuous real numbers, and if it is the case, then in that case we are saying that It's a regression problem. During training, we try to learn the mathematical model, and during test, we'll try to predict this value of y, right, corresponding to any new example which is given to me. Fine. And if it is a if that problem is of classification, in that case, this yi will be what? It will be a so if it is a binary class classification, it will be a positive class or negative class or 0 1, right? That kind of information is given to us. So this is a classification problem, right? uh, yeah, I think all of you know that part. So in this case, what are we trying to achieve, right? So we are saying that each of, let's say in the regression case, right? So I'm just diving into directly to the linear regression case. So in linear regression case, what we are saying is that we are trying to predict a label. But how we are trying to predict the label, and during training, what is there, right? So let's say you have a data set like this. So you have a bunch of examples. Let's say in this case, let's say you have only one feature and corresponding label is given to me. So each of this data point here in this space is can be considered as a xy data pair, right? So let's say this is x1 and the corresponding label is given to me. This is x2 y2 x3 y3 and x4 y4. What we are trying to do is, in linear regression, we try to fit a line, right, going through all of these data points such that the error, right, so error is this one. So error between the prediction. So what this will okay, maybe I'll say that. Okay, sorry, I think this is the wrong diagram. That it has not to be like this because we are not projecting it. We are actually, so let's say this is x1, right? This is the point x1 here, and this is corresponding label y1, right? So this is the actual label. And what is the predicted label? If I use this line as a or if we learn this line, right, which is, let's say, y hat equal to mx and plus c. Here in this case, there is no this line is cutting y-axis at 0, so it is, let's say, mx, or in this case, in our case, we are saying that it is wx. So there is an w, which is an unknown parameter here. We will try to learn that. Okay. So with if we try to do that, this is the error, right, in the prediction, because this line gives me uh, this prediction, which is y hat, y1 hat, basically. And like that, we have some errors if you look at through all these data points. What we try to do is we'll try to find out that line. So we can find out infinite line through these data points, right? We'll try to find that line which gives me this minimum error. So what will be the error? Error in the prediction will be, basically, it is y hat minus y, right? uh, that is actual error. And we will sum all this error along each of the examples, like all through all n examples, and we'll try to predict or we'll try to minimize this error. So this is my objective function here. We are trying to minimize this error. In this case, in linear regression case, we take the squared error loss. Fine. We take the squared error loss. We can take another loss, which is maybe the absolute error also, but we are taking here the squared error loss. Fine. I hope until this point everything is clear to all of you. Y hat I is the prediction which is given by this line. So for each of these data points, if you look at it, right, this will be the another. So this E2, this E1, and E1 is basically is what? Y1 hat minus y. E2 is y2 hat minus y, like that. And we are taking square of each of this terms, and we are summing up that errors, and we'll find out that line. So we can actually have, okay, let's say this is also is the line, right? There is another line here. We'll try to find out that line which will minimize this error, basically. And you can see here is that this y hat, right, which is a line passing through all of this data point, is a function of x and w, right? X is what? Is the data point given to me. What is unknown here? W. So when we try to find out that line which gives me the minimum error, in this case, y hat will be what? So y hat will be, let's say, this case, right? So it is a minimum of, sorry, this is minimum of summation I equals to 1 to n. Y hat is your w transpose xi minus yi whole square. Fine. Uh, right. So if in terms of, if I write it in terms of summations, it will be like this, right? Or in terms of the vectors also, I'll show you in terms of vector how it will look like. So basically we wanted that array. And okay, that I'll tell you about. So here I know this, right? And I have the information about xi, I have the information about corresponding labels. What is I am not knowing is w. So basically this problem is, when I say that I'm minimizing this error, so the objective function here is to minimize this quantity, which is the squared error loss, right? Minimizing that. But basically inherently what we are trying to do here is we are trying to find out that w which minimizes this error, right? And that's why. And what is the what should be its corresponding, okay, or what should be its uh, this w will lie in which subspace? In rd subspace, right? Is that fine? I hope till now everything is okay. So
Yes, sir.
right, no issue still here. Why we are doing all of this is fine, right?
Yes,
W's,
sir.
all of you understand the dimensions of w, dimensions of x, and dimensions of y. No confusion there. If you have, then let me know. You can stop me at any point of time. Fine. So this is the square loss. So what I'm trying to achieve here is we are minimizing this w, sorry, minimizing the square loss such that I should find out uh, the uh, the 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 w which minimizes this, right? Okay, fine. And if I wanted to write this statement is equivalent to the statement finding out the length of this vector x transpose w minus y square, the length of the square of this vector x transpose w minus y. Is that fine? This is okay? Sorry. Uh, any
Yes,
doubt
sir.
here? Anyone is having any doubts here? This statement, when I try to say that minimizing this part is saying, is kind of saying that I wanted to find out that w which minimizes this thing. This is in terms of the vectors. Okay, anybody has raised a hand? Or yes. So w in two dimension can work as a slope. What is it? What do you mean by in two dimension can work as a slope? Can you just elaborate a little bit about it?
So two-dimensional means if take x and y coordinate,
No, no, no,
then W work as a slope.
no, no, no. It is not like that. Okay. Okay, two dimensional means, okay, it's not like that. Suppose, let's say you understand this part. So this is
Yes, yes, sir,
x, right?
clearly.
This is y, right? This is x and y. So here x is in how many dimensions? So each of the feature here
Yes,
is in what is the dimension of x here? So let's say if I have this data point here, x1, and corresponding label is given to me. What is the dimension of x1 here? And what is the dimension of y1? Y1 is in R, right? It can take any real number, right? Let's say I have bunch of data points here, and these, let's say, x2 y2, x3 y3, and x4 y4. uh, what is the dimension of x here? One, right? Or I can say it's in real line, right? Because this is okay, x1 is actually here. This is x1, and this is y1. Corresponding y1 is here, right? Similarly, x2 is on this line, and y2 is on this line, right? So x1, x2, all of these values, they belong to this axis, right? X axis. So can you so basically all of x's here in this example, they are lying on the or they are lying in one dimensional subspace. Is that correct?
Yes, yes.
Huh? Fine. So let us say I try to find out a line through this. Suppose the line is going from here. So what I'm trying to find out here is y equal to some wx, right? Slope is zero. Sorry, not slope is zero. The intercept is zero. W is the slope, right here in this case.
Yes, sir.
Okay. So can you tell me what equations? So you understand this part? Like let's say this is a prediction here. This is the point. These are all the predictions, right? This is y1
Yes.
hat. This is y2 hat. All of you understand? Okay. So what is y1 hat basically is equal to wx1. Hmm?
Yes.
Y2 hat is wx2.
WX2.
So if this is in real number, this is a real number, this is a real number. Okay, let's try to form a matrix here. Okay, then I think it will be much clearer. So uh, these are some values, right? X1, x2 are some specific values which are, let's say, real numbers, right? So this x vector, if I wanted to find out, or x will be a vector or matrix here in this case. If I
Matrix.
matrix, but fine, but does it have what are the dimensions of this matrix? So let's say you have n examples. They be like this?
Like D cross
Except,
N.
yeah, but what is the dimension d here in this case? One, right?
Yeah.
One, yes.
Correct, right? Because it's each of xi is in R. That means it's in one dimensions. So can I say that it is n cross one matrix? Fine. Or basically it is a vector
Yes, sir.
with n features. And okay, what about y vector? It is y1, y2 up to yn, right? The corresponding labels will be there. What are the dimensions of it? Again, it is n cross 1, right? I wanted to find out these equations. Like let's say I wanted to say that it's y1 equal to w x1, right?
Yes,
Y2 equal to wx2.
yes.
Actually, that is my hope, that I
Cross
should be able
one.
to find out this y1 and y2 in terms of x1 and x2, right? So okay, let us try. So if I do this multiplication like this, let's say these are x1 x2 up to xn, and let's say w1 w2 up to wn, and I should get this part. What is it? Y1 y2 y3 to yn. Okay, the dot product between these two, is it possible between x and w? So let's say it is this is n cross 1. I need again the dot product. I should need I need it in my n cross 1. So how this will be achieved? What should be the dimensions of w in this case?
One cross.
1 cross n, but 1 cross n, let's say if it is 1 cross n, what will be the result of this? Will not
N cross N.
N cross.
One cross
Yes,
one.
yes.
1 cross 1, okay, that is fine. 1 cross 1 is fine, but 1 cross 1 is what does that mean? 1 cross 1, let's
Scalar.
say. So then that means you are
Yes,
Scalar
a
value.
scalar value.
so what you are saying that uh, this has to be there, right? Let's say,
Yeah, yeah.
right, that means there is only one value uh, available here to get my uh, this matrix, right? So in this case,
Mm.
if I just multiply with this w, that will be fine. Suppose your x was not in one dimensions, it was in two dimensions, right? So let's say these are the values x1 2 x21 x22, and let's say x and 2. Fine, right? These are the two features, let's say f1 and f2. Fine. What is the dimension of this matrix?
N cross 2.
N cross 2. Okay, then what should be my, and this is
2
fine, right?
cross N.
labels will be fine, right? Labels should be okay. Yeah,
N cross 1.
Yes,
Yes.
sir.
right.
2
Now
cross
what?
1. 2 cross 1.
2
2
cross 1.
cross 1 matrix of W vector.
So what does that mean?
W1,
Like
W2. W1,
W1 and
W2.
W2, right? You need this thing, and then what? How does it look like? Then can you tell me? Like it will be W1 X11,
Wx1 plus W2 x2.
Is equal to
WX1,
Yes, sir.
Y1.
This type.
that is Y1, right? So that's going to be like this. So
I have a question here.
yeah, no,
Why? What?
don't wait 1
Okay.
minute. You ask the question later on. Just
Okay.
let me
Okay.
finish this. So what? Okay, in this case, each of xi here is in what dimensions? Each of the
Xi.
Two
2,
dimension.
2
2 dimensions,
dimension. R2.
right? Because here you have one and here, so each of the vector here is in 2 dimensions. Is that correct?
Yeah.
Yes.
Yes, sir.
All of you are okay? Okay. Each of yi is in how many dimensions?
1.
One.
Yi is
One
1
dimension.
dimension.
Yeah.
One
1
dimension,
dimension.
right? Okay.
R.
What is the dimension of w?
Two
1
dimension.
dimension.
2.
2.
Two. Yes.
This is a w vector, right?
2.
2 dimensions. So what we are saying is that the dimensions of w should be equal to what? The dimension of each xi, right?
Dimension of W?
See, that has to be true, right? Otherwise then
Ah,
this
yeah.
And dot product, no?
huh? Correct, right?
Hmm.
Right. So that means each of xi will have the same dimensions as that of w. Now, if okay, and what we are trying to do here is we are trying to find out its dot product, and we are saying
Actually, W transpose is two dimension, right? W is one dimension only.
w is in 1 dimension. How come you're saying that w is in 1 dimension? This is the entire vector is w, right? So w vector is basically is this one, right? W1, W2. This is what we are saying is this matrix is actually so if I have each of xi, so each of xi, okay, let's say x1 will look like this, x11, x12, two components. X2 will look like this, x21 and x22, right? Two feature, if you have two features, right?
Yes.
This
Yes,
matrix,
sir. You're right.
yeah, so this matrix which you are seeing here is not a x matrix, this is the x transpose matrix,
Okay.
right?
Okay. Okay.
So you are actually keeping each of this variable or each of this examples like this. So your basic x matrix will be like this, x11, x12, right? x21, x22, x31, x32, and it will go up to xn1 and xn2, right? And then you have your w matrix as like this, or vector basically w1 and w2. So now you have this matrix x matrix as what are these dimensions? 2 cross n, and this is 2 cross 1. Fine. You are actually making this x matrix as a transpose, so it will be x transpose, and that will look like this: x11, x12, x21, x22, and then it will go to xn1, xn2, right? And then you have this w1, w2, and this is your x transpose. Okay, I'll write it down here. X transpose, this is your w, and whatever you are actually getting, right? So the product will be it's n cross 2, and this is 2 cross 1. So the product will be n by 1, which is your we are hoping that it should be equal to y, but it is not equal to y, it is y hat, right? Some approximate solution. Fine.
Yes, sir.
So whatever uh, right, so this is, and what we are, and okay, so what is the error between these two? Error between these two will be basically we are trying to minimize this, right? The approximate solution we are getting, this is the approximate solution, right? And this is the actual solution or actual label, right? You're trying to minimize this error for across all the things. So if I uh, if if I just take this as a vector, right? This is a vector of n by 1, right? Y is also a vector of n cross 1. So in terms of the vector subtraction, how does it will look like? So it will be y hat minus y, right? The length of this vector square. That will give me what? And this 2 here is actually saying that it is a L2 norm, right? Euclidean norm or L2 norm. This is my y hat minus y. This is the error, right? And I wanted to minimize this error. Fine? This fine? This is fine?
Yes, sir.
But y hat is basically nothing but this quantity. I have this x transpose w. It can be w transpose x also, right? Both will be same because the dot product is commutative. You can write either w transpose x or x transpose w. I don't think it will change the value here. But fine, we can actually use this one x transpose w minus y. We are trying to minimize this quantity, right? And here I know x, I know y, I don't know w. And this w is in what dimensions? This should be in the dimensions which are it should be exactly the same dimensions as that of your the dimension of each of this data point x, right? So that means whatever the features each of the data point will have. Clear?
Yes, sir.
And this is saying something like this similar statement to say that in algebraic terms, this is what we have seen. It is in the matrix terms, or you can say the vector terms, matrix vector form. In algebraic time, it will be minimizing w over rd such that it is summation of, or we are minimizing summation over all the examples. uh, it is, I can say that I think it is xi transpose w minus yi square. Fine. Okay. So this is a quadratic form, right? This is what we are seeing. It's a quadratic form, right? This is a unconstrained optimization problem, right?
Yes,
Yes.
sir.
Yes.
So this unconstrained optimization problem, how we can solve? We can solve using the calculus in this case. And what will be that solution?
Gradient descent.
No, gradient descent will be, we can see it later. But for example, if you don't want to use the gradient descent, uh, what is your general solution to this unconstrained? So f of x is x square, right? If I wanted to solve this, what you should do? You take the first derivative and equate it to 0, right?
Yeah, x transpose pseudo inverse xy.
Yeah, but how that will come is like this.
Optimization.
Yeah, this is an optimization problem. I'll use the calculus. So since it is a higher dimensional optimization problem, right? It is not a single dimensional problem.
Yeah.
We'll have to find out its, uh, you know,
Derivative. We will take derivative with respect to w, and we will get
yeah,
2x
that will be
transpose
your
w minus
gradient of. So
gradient of f
yeah, what is the
of
objective function here? The
objective
objective
function is
is like this:
x transpose w minus
y
y the whole square.
whole square. But this x transpose w minus, so it is a vector, right? This is a vector. X
Yeah,
transpose w
yeah.
minus is a vector. So and we are taking it square. How do you write it down like this? It can be written as x transpose w minus y
W
transpose
minus y transpose
and
x
x
transpose
transpose
w
w
minus y.
minus y, right?
Yeah.
Right. Now this is your function, or this is a function of w, right? Because x and y are the const, like we know them. The only unknown here is w, right?
Hmm.
If I have the data set with me, everything is known to me. The only thing is not known is w. Now what should I do? I should take its gradient. The gradient of f of w will be what now? So you just think of this. So it will be like 2 times. You just try to differentiate with respect to this.
2 times W transpose X.
2 times
W transpose X.
double transpose x, or
X transpose X. No?
2 times x transpose w
okay, I don't know.
minus 2xy is equal to 0.
Okay, you can do that way also, or you can actually do it in a like you can expand these terms if you want to. Then you can
The
solve.
expand this term, it is better
Okay,
expression so that
that is
how to
not
get
like
this.
very difficult. So you just, if I this transpose sign goes inside, what will happen then?
And w transpose x
X minus
minus
y transpose,
y
right?
transpose
Into
into x transpose w minus y.
so if you just again expand it, what will I get?
W transpose x transpose w.
X transpose, let's say w, or basically it will be your square of
Same.
w, right?
Yeah.
It will be w square if you know it, because right. So and what will be the next part? It will be you can do
W
like
transpose
yeah.
XY.
W transpose xy
Okay, w transpose xy, then it will be y
minus
transpose.
y
Minus y
transpose x
transpose x
transpose w
transpose
So
w.
I'll write.
minus
Okay, can I write this as xy transpose? Kind of saying that xy transpose, fine.
Yes, sir, it is same.
Yes, sir.
Xy transpose w, and then what is it?
w
Y transpose y, or y square.
minus plus y transpose w.
Okay, plus or minus. Okay, fine. And then we
Yes,
are,
sir.
this is f of w, and now we differentiate with respect to w, right?
W.
So that is called so gradient of f of w will be what? So for the first term, if you think it's a square, right? It's a square term basically. W transpose w is w square, right? Correct.
Yes, sir.
So if I differentiate it with respect to w, it will be 2 times. I'll get xs transpose w. Fine.
Yes, yes, sir.
Is that fine?
Yes, sir.
Yes, sir.
What about this term? It will be xy.
XY.
And what about this?
XY transpose.
Xy transpose. Or
Yes, sir.
you can actually think about this xy and xy transpose will be, it will be same basically. And what about this term? It's going to be 0.
Zero.
Zero.
Zero. Yes, sir. It is orthogonal.
See, xy and xy transpose are that's going to be a a transpose. It will be a symmetric matrix. So anyway, it will going to be the same. So what I'll remain with w
Two
and
x x
minus
transpose w
w
minus
square,
two x
and I'll have to equate it to
zero.
0, right? Now
Zero. Yes, sir.
what I'll get here, I'll just say that this 2 anyway get cancelled, so x transpose w will be equal to 2xy. Fine.
Yeah.
XY, sir. XY.
Uh,
Xy
only xy. Yeah, right. Sorry,
only xy.
Yes, sir.
y. And then we are actually interested in this solution, right? So that will be, so w equal to, since it's a matrix, it cannot go to the denominator. What we should do instead? We should multiply both the sides by x transpose
XY. Yes,
x
sir.
Inverse.
transpose inverse, right? So x transpose inverse xy, and that is my solution. This is my w star, right? So this is the solution to the problem, which is not exactly the correct solution. It's an approximate solution. If you remember it from MLF, uh, you will understand that it's a approximate solution, right? Because the w is not in the uh, or it actually it lies into the span of x. Fine, but your y is actually not lying into span of x. If it is lying into span of x, then the error would be equal to 0, right? But here error is there, and that's why we cannot say about it. But generally what happens is, if this matrix, right, x transpose, if uh, and if okay, to have a matrix, or to have an inverse of a matrix, then matrix has to be non-singular, right? But what if,
Non-singular.
but what if the matrix is singular? So can't we get a solution to that? Actually we should get it, and that we should get it through uh, this quantity. So that is called as a pseudo inverse. Fine. So that's the final solution we are getting. This is good because we are getting a solution w star here, and that solution uh, is this one, right? And you can think of that this solution is a what do you say? It's a function of what? The data points and labels, right?
Yeah.
The data points and labels. And if you recall it, for PCA problem, right, W star was also kind of similar to this. The only thing which was missing there is what? The labels, right? It was not multiplied with the labels, if you remember
Yes,
it.
sir.
right? So
Mm.
yeah, so that is what it's different. So what the same thing we are actually doing here, what we did in PCA, we used to project every data point onto the line, right? And then we'll use to find out the solution for that. The similar thing is there. The takeaway from here is what, uh, again, okay, so this is fine. uh, I think one day I have explained about this. Okay, this is what the solution looks like, but how the solution will look like, that we need to find it out, right? So where this W star will lie, geometrically, fine. uh, we'll try to visualize this. Okay.
Yeah.
Yes, sir.
Okay, so I said x is what, how does x will look like, can you tell me? What was that? It was x1, let's say for two-dimensional case. How was it? It has,
X1,
yeah, two components,
X1,
right? X1,
X1,
X2.
2.
this is x transpose, right?
Yeah.
uh, X transpose is x,
X1, X2,
then x21,
X,
X21, X22.
X21, X22, X31, Xn1, Xn2.
right? This is how it will look like. uh, this is feature 1 and this is feature 2. Is that fine? It has two features, right? So each of xi will be in R2. What does it mean? The data point lies in two dimensions, so that means it has two features.
Dimensional, yes.
So it is a two-dimensional data, that means it will have two features, right? And how many
This is the
y's should,
two. This is the two feature, no? X11 and X12. This is the two
no,
feature.
no, there are two features, f1 and f2, and these are the values, right? So basically I have written it here like x11, x12, but in actual practice it will not be like
The
this, right?
first data point and first feature is
I will tell
X11,
you.
na?
Okay, I'll tell you what
Okay.
I'm
Okay.
I have written here. Let's say
Hmm.
there is one person. Let's say first person. I have measured its height and weight. Fine.
Hmm.
It's his height is, let's say, 150 centimeter, and weight is, let's say, 60 kg. Right. This is height and this is weight for the first person. X2 is with height, let's say, 160 centimeter, and
60 and 70.
let's say 65, whatever,
Hmm.
right?
Hmm.
So
Okay.
if I wanted to make a matrix out of it, and let's say how that will look like, either I can write it
150,
like
60.
150 60 and 160 65, right?
Yeah.
Is it?
But
But what are
yeah.
the features are here, right? This is
Yeah.
f1 and this is
Features, horizontally features. Yeah.
f2, right? Now if I write down its transpose, how this will look like? It will
Yeah.
like
150, 60 and 160, 60.
160 and 65. And what is this? Feature 1,
F1,
which is
F2.
height, and this is f2, which is the weight. So this
Yeah.
x11 is which data point? This is x11, this is x12, this is x21. So what is this corresponding to? The first example and its first component, right? First example
Hmm.
and second component. The first component refers to height, and the second component refers to weight. That we know as a human, but how does this computer will understand? It will understand only through the numbers, right?
Numbers.
It
Number.
will not understand exactly what are these points. Fine, right? I hope this is understandable,
Yeah.
right? So now my matrix looks like this, X transpose matrix. These are the features, and this is like, this is feature 1 and this is feature 2, right? Fine.
Yeah.
So can I say that this X transpose, okay, X transpose, X transpose matrix will look like how? It will be some numbers, 150, 60, 150, 155, let's say 65, 160 centimeter, let's say 70, 165, let's say 65, like this. Fine. These are all, let's say this is height and this weight. Fine.
Hmm.
Is that okay? So height I'm calling it as f1, and weight I'm calling it as f2, right? And their corresponding labels are, let's say, body mass index. Okay. Let's say body mass index is, I don't know. Let's say I don't know, maybe point 0.5 or something. I don't know. Let's say it is weight by height or something, or height by weight. I I don't exactly know the formula for it, but I'm just assuming that there is some quantity I wanted to measure, and this is 0.5, 0.55, 0.65, and like that. Fine. Okay. What we are trying to find out the approximate solution as W as some values or some uh, okay, some values. Okay, what is the dimension of W in this case now? Can you tell me? How does this
Two.
equation look like? Two,
Two
right?
dimensional, yes.
Yes.
W1, W2.
This is W1, W2. If I have, I can like, so the first equation will be like this, right? Y1 hat equal to 150 W1 plus
W1.
60
See,
W2,
W2.
W2, yeah.
right? Y2 hat will be 155 W1 plus 65
65 W2.
W2, like this. So can I say that it is kind of solving linear equations or those the simultaneous equations, if you remember, right?
Yes, sir.
So I am actually trying to solve this problem, and then I'm saying that this y1 hat should be equal to y. But is it going to be true in practice? No, right?
No.
There will be some error, and that error I'm actually showing it like this. Fine.
A
So we
square,
have,
yes.
so how many equations do I get here? N equations, right?
And question.
We are trying to find
Yes.
out q, which is only of two dimensions. Okay, right. So if I, okay, what we, but let's say instead of seeing that x1 as a feature, right? So this is x1, right? This is my x1, this is my x2, this is my x3, and this is my x4, right? Is that correct? Or can I
Yes,
say
sir.
it is x1 transpose of
Yes.
vector, right? All of these are the transpose of the vectors.
Yeah, transpose.
And but see, if I don't see these vectors individually, like x1 transpose, x2 transpose, x transpose, x4 transpose, like that, instead of that, what I'll do is I'll see this as what will be this vector, f1 vector or height vector. It will be, what dimension does it have?
N cross
Which
1.
which which vector?
Yeah, f1 vector, the feature one vector will have
N plus 1.
n cross 1, right? So it
N
will be
cross
like,
one. Yes.
Yes.
it will be all the heights, right? Here it will be all heights, so it will be n cross 1. What about f2, which is a weight vector, is again n cross
N
1,
cross 1.
right? Okay, now you are understanding the point. What we are trying to do here is we are actually taking all these values and making it as one vector. Fine.
Yes, sir.
Okay, I hope it is understandable. There is no issue about that part, right? Okay, let us
Yes.
try to visualize this f1 and f2, uh, and where this f1 f2 will lie, right? So your f1 is this, let's say, and there is one f2. So each of this f1 f2, if I just try to plot it, correct, it will be, and if I wanted to say that there is this y is what here, these are all the labels, right? They are also n cross 1. Can you tell me how should I write y as the combination of f1 and f2? Can I write some combination of f1 and f2 and find it out which y?
Y is actually the linear combination of F1 and F2.
Right.
We have to multiply by some vector.
Yeah,
Then
but
we can get
what will be that vector? Let's say that vector is alpha,
that vector. Say this is n cross one.
right?
That vector must be one cross uh, n cross one.
Hmm. What is the dimension of?
Then only one scalar we will
Okay,
need to
okay.
multiply.
Maybe I'll write down like this. Let's say
Only one scalar is required to multiply.
no. Alpha f1 plus, let's say alpha 1 f1 and alpha 2 f2. If I write down the combination of this, can I get y? Is that fine?
Yeah,
That is fine, right?
Yes.
yeah,
Okay. What is the dimension of y here? It is n cross 1.
n plus one.
Dimension of f1 is n cross 1.
N
Dimension of
cross
Because,
f2 is n
yes.
cross 1. So if I wanted to maintain this, right? So this alpha 1 f1, the product should get what? They should also get the n cross 1, right? Out.
Yeah,
Yes.
Okay. Then how do I get it? That is the question here. will okay. You are saying that correct. It should be a scalar, right? It shouldn't be the
It
vector.
should be a scalar only because we
Ah,
need from n cross 1
right.
to n cross 1 that the only solution is the multiply by the scalar, either one scalar or give a combination of a scalar.
Correct. So not combination scalars. Actually, only one scalar is required. So I'll write it down here. It will look like this. So this is your f1, right? Feature vector one.
Yeah,
And let's say I'm writing in terms of the matrix is f2. Then you have
Into alpha 1, alpha 2.
alpha 2. Fine. Is that okay?
Yes.
yeah. The
Yes.
scalar will depend on the number of features. Whatever be the number of features,
Yeah,
the
that is
scalar
okay.
must have the same number of dimensions, right?
Right. That is fine. That is correct. So I agree with this part of yours. Let us try to say that uh, with these two features, right, f1 and f2, what are how many linear combinations I can get in here? Or can I? Okay, leave that part also. Let's say uh, this. What is the first row of this matrix? This
X1.
x11, x12, right? The first row.
Yeah,
So I'm just what trying to do here is I'm trying to find out this alpha one x11 plus alpha two
and
x2
alpha 2, x2, 2,
one two,
x1,
right?
2.
Right. So some combination I'm trying to find it out. So can I say that it is nothing but x transpose alpha again?
Yes, sir.
Yeah, it's the external.
Okay, fine.
From the matrix itself, it's obvious. No?
Right. Yeah, that's what. Yeah, that is correct. And now let's say these are f1 and f2. So the linear combinations of f1 and f2 will be where? So that will span what? That will span this x f1 f2 plane, right? Maybe I'll just draw it differently.
Something wrong.
Nothing is wrong here, but
Just go up, scroll up,
yeah.
scroll up. Y is not equal to X transpose alpha.
What is it?
Y is not equal to X transpose alpha.
That is also fine, right? What? How does it will differ? It's a dot product, right?
How do you express Y in terms of omega? Sorry, W.
Uh
Y is equal to X,
Y is equal to
X transpose W, right? That's what we started with.
yeah. That was okay. That was what. So
We
we
started
were yeah. We started with that part, and
No, wait. If Y is equal to X transpose
yeah,
W, and
yeah.
that is also equal to X transpose alpha,
Hmm.
what is the difference between alpha and
There
W?
is no difference. That is what we are trying to prove here. You are
No
saying,
difference.
yeah, whatever you are saying is correct. But what we are doing it differently here is that instead of so what will be the space of x? Okay, I'll show you then
Wait. The
differently.
question is, if alpha and W are same, why are we bringing in the name of alpha and confusing it?
Okay, I'll tell you. No, not confusing. I'm not confusing anything
I
here.
know. No,
There is
no.
a different perspective here to
It's a
see.
different perspective. It should be the other way.
Yeah, let us say your x was in what dimensions previously?
The way I understood is W is to correlate the features to the output,
Right, right.
whereas alpha is supposed to pick up the data set to the output.
What does that mean? I don't understand.
Just go through that. You will get somewhere. You will get stuck and probably then correct.
Okay, no, no, I'll get through it. Just give me a minute. Like I'll try to explain to you why we need this f1 f2, right? So let's say your x was in RD, right? In that case, your w was also in RD. There was no issue in that part. But if I
Just put
tried
dimension. Put the dimension, then we will realize.
right, so
See, W is supposed to be D by 1.
yeah, right. It's a vector, d cross one vector.
Correct. Alpha?
Alpha also has to be d cross one vector.
No. Alpha is N cross 1.
N cross one.
Yeah.
Yeah, I also agree. That
No,
was
no,
the
no, no,
question.
no. Alpha cannot be n cross one. It has to be two d cross one only, right?
It's
But
not.
once we convert the feature vectors, no?
Ah.
then it becomes n cross n solution.
No, 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 no. I think you're confusing there. It's
Okay, let us do it. How it happens.
you're saying what you're doing, trying to do here is you're actually okay. I understand what you're trying to say here is uh, fine. So I think you're just saying is that let's say you have n cross one. So let's say this
Because
was
we are transposing, we are converting
Whole,
data points into the feature matrix.
okay.
We
This
are
will be like
creating feature
wait
matrix.
a minute, wait a minute. The whole purpose of going to alpha is only when we find the d larger than n,
uh,
instead of figuring out w, which is going to be d, let us go in the other way, the dual. Basically, it is a dual. We transpose it and then figure it out what is an alpha, which will be lesser dimension. Then we link using the mapping. That is what we do all the time. We look for the least dimension to work on.
that is a different case. Don't you think that is a different case you're
It
just talking
is
about?
not, because there is no need to bring in alpha today. If you have got to still work in the same
Okay.
d dimension, then why are we talking about what the alpha is going to give me additional?
Okay. Fine. Okay. Fine. I. Okay. Let's try. Let's say that I'm agreeing with you with this part.
No, no, it's all right. Let's figure it out unless alpha is going to help me out. Look, if it is alpha is the same as W,
Uh,
why do I need an alpha? Why should I mean, whatever alpha is going to do, W can do. Correct?
that is true, but see how you are. Okay, why we need that alpha? I'll tell you. Okay, maybe that is a question here, right?
Yeah.
How to visualize that into? So we need that is for visualization purpose.
But if
Okay.
they're same, why
Uh,
can't I visualize using W itself? If they are same, that's my
yeah.
point.
Correct. Correct. So
If
let us
they are
see.
not same, what
Yeah.
is the difference? And that is what is likely to give me some additional
Fine.
intelligence.
Okay. Now let me tell. Okay. Let us see this. F2 is in this format, right? Like let's say F is x21 and then x22 up to xn2, right? This is fine.
It's n by
Yeah,
it's n by 1. Always go by the dimension. That is easier.
Okay.
yeah, n cross
If
it
you
is
are
n plus
defining,
one.
yeah, F2, but if you're defining it as a
Uh,
put together, then it becomes the X transpose. That's all right.
that is okay. So this is correct.
Yeah, that's okay.
These features are fine. And what you are saying is my alpha should be here is like this, right? You're saying that it is alpha 1, alpha 2 to alpha n, right?
Yes.
Your
Yeah,
n things, right? And then you is that fine? Or
and
do
it should not be n. N alpha should not be n. I think so.
then
It
what
depends on where you are introducing alpha.
Yeah, it will depend.
It depends on, basically, it depends on our
It,
definition, right?
yeah,
uh,
We
that's
take
what
alpha to be what? Then it becomes what it is.
correct. So I'm saying,
yeah,
okay, that is what I'm trying to say, right? So I'm just wanted to find why, in terms of these two features, I wanted some, linear combination of F1 and F2, right? So I
yeah.
need alpha 1 here and alpha 2 here. Now let me know what are these vectors or what are these values. Now just tell me. And one more thing I just wanted to. So there is one case I told you is that X is my matrix like this,
This is
where
okay. Oh, fine, fine. Now, can you write Y in terms of a W?
that is what I'm trying to write it down here also.
Okay.
And how I'm writing that, see there is okay, let's try to see this. What was my X uh, previously? The vector of all data points, or maybe I'll just write down it in this fashion. X transpose is,
X transpose.
I'll say
X
x11,
one, X 11, X
and
12.
one x22 and like that to let's say x n1 and x n2, right? Is that fine? This okay?
Yeah, go ahead.
W1 vector is this one, W1 and W2. Fine. Now I'm writing each of Y1. So okay, I'll write down this also. Y is
Again, same thing is going on.
not same. Oh, it's kind of same. See, I know that it is same, but how uh, will you look at it, right? So that is different. Okay, let's see.
Okay,
Y2,
okay. Let us see. Let us see.
Y1, Y2, and let's say Yn. Is that fine?
Yeah, it is
Okay,
fine.
you are saying what I'm saying is that like each of Y1 is actually like this: W1 X11 plus W2 X12. Fine, right?
Yeah, yeah.
Y2 is W1 x 21 plus W2 x 22, right? And
The
like
same,
that, you will go for Yn. So
same
now,
thing on the
yeah,
left side. Why don't you write what you in terms of alpha and f?
Yeah, only the mirror image of alpha and W, no?
Yeah.
Same.
Your f11
huh,
will be x11.
F1.
Yeah.
Okay, that's okay. But now, if I wanted, see, that's what. But
No, no, just write it to the left side, then we will see it so easy.
what
On the
is
left of this,
correct?
y1 equal to
Huh?
alpha 1 into f11, which is x11. Correct?
Alpha 1 equal to x11.
Well, yeah, you're writing alpha 1 is y equal to alpha 1 f1, right?
Comparing the equation that
You
above and the below equation.
okay? But then if I do like this, alpha 1 times x11 plus alpha 2 times x12 x21 will not be. It will be the same as that of writing a w1 into x11, right?
Correct.
I'm
Correct.
not saying that. I'm saying that I'm just multiplying that x with entire feature vector. I'm not that is what I'm trying to say, right? You're
What
not.
do you get by that? Alpha 1 is a scalar, right?
Yes, alpha 1 is
F1
a scalar.
is a
Okay,
vector.
f1 is a vector, and there is one
No, no,
another.
which is nothing but x11, x21, x2, x31, right?
Huh?
What is
Huh.
f1? F1 is
F
x11,
uh,
x21,
uh,
x31,
yes,
right?
yes.
If you multiply by alpha 1, what do you get? Throughout, it will be alpha 1, x11,
Okay.
alpha 1, x21,
Uh,
alpha 1, x31,
right.
which is identical to what you have written in terms of a W.
Actually, what I understand is that
No, no,
we are here.
Got it.
X.
Yeah, yeah,
stop.
got it. No, no,
Just,
whatever he is saying, I understand it. Okay, there
no,
is.
no, just write in alpha terms what
Okay.
is y1 and y2, then compare.
Okay, fine. Okay. Just do one thing. Okay, we are actually going into. Okay, maybe I am getting confused with this. What you are trying to say, but see, what we can do is maybe I'll
First
stop.
you first you do, sir. Then we will discuss.
Yeah, what I'll do is I'll stop it here. The discussion.
Yeah,
Maybe at
that's
the
okay.
end we'll
Yeah,
continue with
Yeah.
that.
this will
I
digress
think,
otherwise. Go
yeah,
ahead.
I think I'm missing something here. I just wanted to say something
I
else.
see
I'm
that. I see that.
forgetting
It's okay.
that.
Take a break.
Yeah,
Change the
yeah.
problem.
So
Yeah.
yeah,
Change.
maybe because other students are waiting for that to complete it, right? So let me finish this for right now, and then we'll again come back at the end. Fine.
Yes. Yes.
I think the way I wanted, I think initially I started, it was something different, and I'm like now myself I am getting into all of this.
And it's okay. It's
It's
all
fine.
right. It happens everywhere.
Okay.
Don't
Yeah,
worry.
fine.
Don't
That's
worry.
okay.
Change the problem.
Okay, let's okay. We understood this part until this part is fine. That was x transpose pseudo inverse xy, right?
XY. Yeah. Here it
That
is.
was fine. That was my solution to the linear regression problem. I think
You wanted to explain geometrically. You were.
right. So no, that geometrical part I'll leave it for now because I think
Okay.
that
Fine.
is what
Okay.
we are getting stuck, right? So that is
Okay.
okay. We'll move ahead from this
Okay.
problem.
But let us proceed.
So for now, we know that this is going to be the solution, right? To solution to the problem, which was the unconstrained problem initially we thought of, and that was the minimizing the squared error loss. That is fine, right? Now, this okay, we can actually find it out. This is easily find it out by using the linear algebra, right? We know how to find out its inverse, and we know how to get all of this done, right? In the uh, by using the linear algebra. So we have a lot of linear algebra packages which we can do, and we can use it to find out W star. But the problem here is what if you are matrix X, right? So when we deal with the real life data, right now I think we whatever the data we are using, right? It will be like with the huge uh, features, right? So the machine learning itself or the data science is actually the science which we are actually using for the large amount of data. And when we have that large amount of data, when I say the large amount of data, that means each of xi, right, which is having d features or of its d dimensions, if that d is very large, then finding out this expression, right, which is xx transpose. So first of all you will need to find out its what uh, this dot product between x and x transpose, right? So that matrix, first of all, you'll have to do the dot product, and then so that dot product will be of this, right? D by D matrix. You will get the D by D matrix. That many computations you need to do, and later on you'll have to find out its inverse, right? So this process of finding out its inverse and then finding out the solution, right? With the large D, let's say in thousands, right? If you have your data set is having like 1,000 features, 10,000 features, then finding out this will be a very difficult task for any good package also. So instead of that, people what they use is they use the gradient descent method.
Gradient descent.
Yeah, gradient descent method to solve this problem. Fine. Is that okay?
Yeah.
Okay, in this case, when I wanted to find out its, or we wanted to apply this gradient descent, we all know what is its update rule. So the update rule we use is WT plus 1.
W1 is equal to WT minus eta
WT
t,
minus
gradient of
yeah, eta t, if basically it is a function of step sizes and gradient of f
gradient
with
WT.
WT, right? That's fine. Okay.
Yeah.
This eta will be your step size. So we already have found out what gradient of f previously, right? What was the
Yeah.
gradient of f?
2xx transpose
Yeah, 2
WT
times.
minus 2xy.
Sorry, this is yeah. This 2 times xx transpose. Array. This 2 times xx transpose w minus 2xy.
2xy.
Right? This was what your w. Uh,
Gradient.
then this was your gradient, right? Correct.
Yeah.
So now and then that should be at each step. So it will be, let's say if it is a teeth iteration, this will be your teeth iteration, right here. Okay. Then how does this update will rule will look like? Will wt plus 1 equal to wt minus eta t,
Eta t
and that this will be let's say
into
this will be 2 times
2xx transpose
xx transpose w minus
t minus
2x,
2x.
and basically it is, let's say, t.
Hmm.
I achieve something significant from instead of writing this out. We know that, right? For if the function is convex, in that case we definitely get the solution to it, right? Or
Yeah.
we'll get the minima. We can achieve the minima using the gradient descent that we have studied previously. If somebody has taken MLF in the previous term, they might not know. If not, I'll tell you that the y minus x square, right? Sorry, y minus y hat square, that squared error loss, it's a parabolic function or quadratic function, right? It's a
Yeah.
convex function. And when you have a convex function with the gradient descent, it will guarantee that you will reach to the because it will have a global, so
Global
yes,
minimum.
you will reach it to the global minimum. That is guaranteed by using this gradient descent
Yeah.
method.
Yeah.
So we can achieve this in t, like let's say finite number of iterations, right? So initially, when you see this, we need to do these calculations previously. Okay, it was order of d cube calculations you need to do there. Here
Hmm.
you see that in this uh, gradient descent rule, we don't need to do that all the calculations because that inverse part is removed, right? We just have to do this x6 transpose and w2. So just dot products you need to find it out, correct?
Yeah.
So now we if you have so let's say you have the d very large, that is number of features are very large. In this case, this method in finite number of iterations we will be able to uh, find out its solution. It will not you know this was these calculations were actually going in d cube, order of d cube. This is actually much better than that, even though it takes t steps, let's say, but those t steps are the finite number of steps to reach the solution. So this is much faster than the previous step which we actually using which we were using the linear algebra methods to solve it, right? Or linear algebra packages to solve this. Fine. But okay, this is also good thing. But now there is another problem, that so each of x is actually is what are the dimensions of x? This is a matrix of dimensions n cross d, right? Or d cross n, right? D
D
cross.
cross one.
Yeah. So now the problem here is, let's say if your n is very large, n is very large, that means what? You have huge amount of data. So the
Mm.
number of examples are in millions, right? So you have collected millions of uh, data with d features, right? In each of this example, in that case, this calculation, right? This calculation
Mm.
or this calculation, both of these calculations will become, uh, again it will consume much of your time to solve the uh, problem again, by using the gradient descent method also. So gradient descent method was doing better if you have d larger. uh, it was doing better than this linear algebra method, which we were seeing, because inverse computations are not there. But still, if you have n large n, in that case, we this method also will take some amount of time, right? So if you understand that, if you are a computer scientist, or if you wanted to uh, each of see, if the time consuming to get the solution, right, if it becomes higher, what will happen is its computational cost will get higher, right? So you don't want to bear that cost. So that's why, even if we use a gradient descent method, if the number of examples are large, right, again these computations will become time consuming. So there is another method to solve this kind of problem, and that method is what? Stochastic gradient descent, right? Stochastic gradient descent. Basically, this is kind of a batch gradient descent. What you do is, you take a sample at random, right? So your data is of this d cross n, right? Of that size. What you do is, you don't use entire data at a time. So you do, that means you don't use all n examples at the time for this gradient descent. What you do is, uh, you use some of the data, right? You pick the data randomly, and you use some of the data. uh, what do you mean by, let's say you have n examples, and you pick randomly the k data out of it, right? So k examples out of it, and here k is smaller than n, right?
And
Fine. And what you do is, you try to find out, again you apply the gradient descent over this batch, right? Batch of k examples. Fine. Batch of k examples, and you do it for each time step. You do it for randomly selected batches, and you take the average of it, right? So after t rounds, you will get that average. Again, the del f of w here in this case will be what? It will be similar, right, as that of this x is transpose w minus xy. The only thing is, this x is not entire thing, it is of k batches. So we use this tilde right here to showcase that this x is not entire batch. Instead of that, it is a sample of that total number of examples. And after t rounds, what you do is, you average it out uh, for all this. So whatever the w's you get, right, updated w's, you take their uh, you take their average, and you find out the average. So average, let's say w, and that w, average w, is called as the stochastic gradient descent. Is that okay? That is at capital T. Fine. So what is the
Sir,
difference?
what is the here?
Sorry.
What is the in the denominator?
That is total number of iterations, right? Here.
iterations.
Yeah. So here t will go from 1 to, let's say, capital T. So let's say in each time, right? If you uh, look through, uh, okay, each time, so there are like total of t iterations, right? Capital T iterations. Let's say you have done 10 iterations. So at each iteration, you didn't take all of the data. What you do is, you take the sample of data, and you do it for, let's say, 10 times, and each time you get some w, right? So you get, let's say, if this is t equals to 1 to 10, you get w1 by using that k of the data. So it is k is selected randomly, fine. K is selected randomly out of the n. So you get w1, w2, w3. If you iterate it for like 10 times, you will get 10 w's. Now you do it, what is, you just take the average of it, and the average will be looking like this, right? By 10, fine. So this t is equal to 10 here, and that
Yes.
entire average is called as the SGD, or stochastic gradient descent, W. So that means you are finding out the, you're not actually getting the W. So what actual W should be? It has to be equal to that W, which we have seen previously, right? This
Yeah,
one,
W star.
or yeah, W star basically, or you can say that that has to be come out of this calculations. So when we take all the n examples for the calculations, but we are not taking.
It should be equivalent to that, approximately.
Yeah, yeah, it should be equal, but it will not be equal, but it will be
Yeah, yeah.
very nearer.
Near, very near.
Yeah, so
Batch side, whether batch side should be same or it may be different also, size of the batch.
I so it,
Randomly,
no, it is
uniformly
dependent.
random.
Yeah,
Huh?
it will be dependent. So there are, so I think you're going to learn that in MLP. So batch sizes can vary. A batch size can be same. So for this course, we are saying that this batch size is same. Right?
Okay. Okay.
Okay, that's okay. I think that is fine now. Okay, one more problem remaining is what? Till now what we were seeing is, um, your your data set, right? Or your data set was lying, okay, your w star, let's say w star was there. Okay, I think
In
that's
in
for
the
that we get
in
to
the in, in,
understand.
in the SGD also, it is guaranteed to converge, right?
Yes, yes, yes.
Right. No?
Yeah, it will be like, it will not be exactly the same w, but it will be nearer to that. So
Yeah.
but it will also give you the correct thing.
Mhm. Mhm. Okay.
Okay, fine. uh, right, so this is fine. I think I
Yes.
will, yeah, I think I will take. There is one problem of nonlinear regression, right? I'll maybe, I hope you remember it from. Okay, so for this part to understand, right? Again, you need to know that,
Geometry.
yeah, geometric representation. So
That
this
is required. Okay.
nonlinear regression, right?
Kernel is directly related to the geometry, I think.
Geometric representation. Fine. Okay. Let me come to that part later on again, because until that alpha is clearer to me also and you also, right? So, so
Make a good note
yeah,
and video for that.
star
It is
should
very
be,
confusing.
yeah. So it's okay. Right? It's not that confusing. I don't know. I was, there was some chain of thought in my mind, and after that I just got stuck there. I'll take few minutes to,
Like have a cup of tea and then done. No
not now.
problem.
No, no, not now. Maybe at the end I'll pick up that kernel regression point. Uh, Before that, we'll finish it off like other things which are there, right?
Okay.
Right. So now we'll see the probabilistic view. I hope all of you know that also. So we are initially we thought like whatever this error loss we are taking is a squared error loss. Now uh, we are saying that given the data, how the labels are generated, we are saying that, okay, generally my x is in d dimensions and y is in this, right? That is what my data set here is.
Yeah. Yeah. One.
So if you think this part, let us say each of this data point is lying here, right? And is in some dimensions. Now here we are seeing is one dimensions only. So there is this line going through it, right? This is not the exact representation of what my lines is, right? So this, let's say, y hat, the prediction line, right? There is some error here between the two predictions. So this is my true level y, and this is my predicted level y hat, for the first example, right? So there is this error here. What we are saying is whenever, so why this errors actually happen in real life. So whenever you take any measurement, right? Suppose I think all of you have done your 12th standard, right? Have you done that experiment of acceleration? So or gravity,
Yeah,
gravity.
yeah,
So
yeah,
you need to find out that value for this g, right?
yeah.
Uh,
Number of times
g is what?
gravity.
Yeah, gravitational acceleration basically, right?
Yeah.
That constant is there, which is we are believed to have that number as 9.81 or something, right? That was
Mhm.
acceleration. So whenever you do experiment, I think all of you have done the experiments there. Do you get the exact value of 9.81 each time?
No, it
I think
always changes.
you roll the ball from some slanted height and you noted down the time, right? And you find out its velocity, and from those equation you try to find out this g. But
Yeah.
whenever you do any experiment, do you get the exact value of g 9.81? No, you get
Mm.
some different values, right? Some distributed values, scattered values, right? Which are, but you never get that g equal to 9.81. What was the reason? Do you think that it is there? It is because of how you are measuring, right? What is the
Yeah.
measurement tells you?
Human error. Human error.
Error might be there. There may be the precision measurement, right? Whatever you are using it, that also may be faulty, right? Or maybe not precise enough to get that value, right? G. But does that mean whatever you are doing is wrong? No, right? You'll have to uh, compensate for that error, right? So that means you are saying that whatever observations you are taking it there, they have some inherent error with that, right? If I reduce that entire error, I should get the exact this value of g there, right? So similarly in real world data, uh, right, there is some errors, right? When you're, maybe human errors or some other errors. What we are trying to say is that this line should be the perfect line, right? What is this? What is the equation of this line?
Y is
W
Y
equal
is
to
equal
plus
to
C.
X.
or W transpose X.
W transpose X plus C.
Yeah, but if it is going through origin, that means that C,
Yeah, 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 yeah. C is equal
can
to
I
X.
say that it is W transpose X. So what we are saying is it is W transpose X uh, plus what? Some error, right? Some error is there. That measurement error is there, and that error we call it as noise sometimes, or yeah, you can just say that
When it is going through the origin, then why this is error?
this is the error, right? So let's say this is my exact y, right? Y, exact value of y. Suppose this is the price of the house, y. Fine.
Yeah, that is okay. That I can understand.
Yeah.
But
So let us
here,
say, yeah, let us say for okay, actual data is like this. Suppose x is my area of the house, and y is the price of the house. Fine, right?
do you mean to say that this line is not always passing through the origin? It may not pass through the origin.
It
Then
will,
only this error will come, na?
no. It's not like that. It doesn't matter that it will pass through the origin or not. That is okay. I'll tell you what exactly it is.
Okay,
So
okay.
let's say this area is 500 square foot, right? Let's say area is in square foot. Price is, let's say 5 lakhs. Okay.
Hmm.
Then you have area 1000 and price is, let's say 6 lakhs. Okay.
Hmm.
Then there is area, let's say 1500 and okay, okay, sorry, I'll do this thing. I'll say that this price is 11. Okay. uh, this price is 14. Fine. Okay,
Yeah.
what do you think about, let's say if I plot these points onto the graph, what do you think the good line should go through? Let's say area is 500 here, then 1000 here, 1500 here. Exact, what are the exact points? So here, let's say it is 5, here it is 10, here it is 15, right? Uh, where, uh, okay, what is the actual data point? Data point here is 505 is here, right? The data point, correct?
Yeah.
1011 is the data points. Maybe see this will cut here, and let's say here, this will cut somewhere here. I say it is somewhere here. Yeah, it is because it is above 10 and below. No, below 15, right? So yeah, it's not exactly 11 also. And what about 1514? It will be somewhere here. Is that okay? Fine. So if I wanted to, if you believe that this price prediction, right, it is a linear regression problem. So the what do you mean by linear regression? The relationship between the features. Feature is where this one is my feature, right?
Yeah, the square feet
Feature.
and price.
No, no. This is a feature, and this is
Yeah,
your label.
two.
Yeah.
Yeah,
So I am saying that or I am assuming that the relationship between the feature and the label is linear. What does that mean is that if I plot a line or if I draw a line, all these data points should go through, or all these data points should lie onto that line. Is that fine?
yeah,
So let us say this is the line, right? Okay, fine. This data point is actually okay. This data point is lying onto this line. Okay, what do you think this line's equation is there? So suppose I'm saying that the equation of this line is y equal
W transpose
2 times, uh,
2 times
okay, or not 2 times. Maybe I'll say that 1/100 times x, right? Or x/100. Is that fine? If say this is a line, what about what will be the prediction for my first data point? This is my first data point. What is the prediction for first data point? Y1 is equal to 100
500
by,
into 500.
so it is equal to 5.
5,
What
5,
is, this is the prediction, right? So I'll say that it is y hat. What is actual y1? 5,
5,
right? What about the second y2 hat? It is 1/100 into 1000.
1000,
So this is my prediction. What is actual y2?
10,
11,
actually 11.
right? And y3 hat will be 15, right? But y3 is
15.
actually is 14. So what will be the error here? This is 0.
There was
So
0, this is 1,
this 1, and this is
this is 1.
1 or minus 1. Let's say however you are
Yeah,
taking.
whatever, yeah, minor.
Fine. But what does that mean is that uh, I I'm actually I wanted to say that all these data points should lie onto this line, right? So that means they should be able to satisfy the equation of line, correct? But they are not doing that because real world data is not like that, right? There will be some error associated with it. What is the error
Mm,
each of this measurement will have? So the first data, what is the error?
0,
What about the second? 1,
1.
and there is minus 1, right? Fine.
Mm.
So if I say that this error is a random variable, correct? Is that fine?
Okay. Error itself is a random.
Yeah, error is a random variable. And
Mm.
when we talk about random variables, we talk about its distributions, right?
Yeah.
So suppose these errors will have some distribution.
Mm.
And I'm assuming that since most of the things in the life, right, they follow the normal distribution, I'm assuming that the distribution is a normal distribution. Fine. Okay.
Mm.
So what I'm trying to say here is this y is right. This y, the labels are generated given x. They are actually they should be lying onto this line, right? W transpose x line, but they are not, correct? This point y2 should be equal to 10, right? And this y3 should be equal to 15. But in reality it is not there, but there is some error associated with it, and this error is a random variable. Okay, this is a random variable with some distribution, and I'm assuming that this distribution is nothing but a normal distribution with mean 0 and variance sigma square. Is that fine now? Any issues with?
Yes, fine.
No, right? No issues, right? Yeah. Okay. So I know this distribution. I know x. Okay. So suppose if this is a random variable, what do you think about this? This also be a some random variable, right? Anyway. Hmm? What is unknown in this case? In this equation, this w is unknown,
W is not.
right? So this in this case, let us try to say that it is the slope of this equation, and this is unknown to me, but uh, this is in d dimensions, right? Because if my xi is in d dimensions, and similarly my w has to be in d dimensions. Okay. Okay, so I need to solve this problem. I don't know w, so how will I get that w? That is the question here, right? So to get that w, since we are assuming all of this as a random variable now, and each of the random variable will have its population density, the data which you have collected, you can think that data as a sample, right? So we know how to find out uh, okay, okay, now it's fine. Okay, let us say that this will be some constant, right? This part should be some
Yeah.
constant, right? And this epsilon is a error. uh, so can you tell me what is the distribution of y given x?
Here W, epsilon, and Y, all the three are random variables, no?
No, epsilon is a random variable, right?
W.
W is not random variable, right? W is a fixed
Okay.
quantity, correct?
Okay, we have to find it.
Yeah, but that I don't know, but yeah,
Yeah.
that is what I don't know. X I know, this
That's I
constant, right?
know. The data point.
Since this quantity is constant and this quantity is random variable, this y given x will become what? Random variable.
Yeah.
Okay. Now, what will be the distribution of this y given x then? It will be normal, right? So
W transpose X comma sigma square.
sigma square, right?
Yeah.
So that will be your mu and that will be your sigma square. So this is normal distribution. So now here, what I don't know is I don't know this w, right? I know everything else. So how to find its w? So we use the maximum likelihood method to or maximum likelihood method to estimate the w, because that will not be a true w, that will be a uh, that will be your estimator only, right? So by using the maximum likelihood method, you try to find out this w. So or you try to find out the likelihood that w will occur uh, given all the data, right? So x1 to xn I know their corresponding labels. So what will be the likelihood in this case if it follows the normal distribution? It will be the product of I equal to 1 to n, and it is e to the power minus w transpose xi minus yi square. Why it is like that? Is normal distribution, right? Whatever I am writing here is a normal distribution divided by 1 upon root 2 pi sigma. And if you find out its maximum likelihood, what I'll achieve is I hope we have done that previously also, so I'll skip that step now. So w hat ml in this case is going to be same as that of your w star, which we have found out using the linear algebra method or by using the gradient descent method. And that has been equal to x6 transpose pseudo inverse xy. You can find it out later, but that is going to be this. So what does that mean is, uh, if you assume the if you assume the noise or the error to be Gaussian error, what will happen? The solution will resembles to what? The solution of the squared error loss, right? If you assume the squared error loss and try to find out the solution by using the linear algebra method, that is exactly be equal to this solution, which we found out by using the maximum likelihood method, assuming that the loss is Gaussian, Gaussian loss, or sorry, not loss.
Error.
The error is the
Error is of the Gaussian distribution.
correct. Fine. Okay, good. So that is fine. Then what is next? Like, okay, we have found out that this is fine, but what is the use of this uh, estimation, right? That also we need to find it out, right? Why we need this estimator and what we are going to gain through
Yeah,
this.
yeah. Why we are learning this?
Why we are learning this part, right? Fine. Okay, and that is going to be done. Okay. Now we have this estimator. What is my W hat ML estimator? That is nothing but your W star. But what is it? It is X6 transpose pseudo inverse XY, right? Yes. Is that okay? Right.
Yes.
But is it and that is equal to W star? But this W star or W hat ML, is it the true W?
Pardon?
Is it a true W?
WML is not true.
W hat ML is not true W, but it will be you know
Approximation of that, the maximum likelihood.
yeah, that is correct, but that is not the true W. True W will comes from your population, right? And this W hat ML is actually uh, it's so let's say W hat ML is dependent on what, right? Can you tell me what is it dependent on?
On data points only.
On data points, right? So if you
And
change
levels.
X, so if you change this data points, this is the training data, right?
You are training.
So suppose let us say we have 10 lakhs of data, right? Or let's say 1000. You have collected 1000 data points, and somebody else has collected 1000 data points, and let us assume that they are coming from the same distribution on the same like with the same features and all, right? They are coming from the same distributions. The W hat ML which I have calculated and you have calculated might be different, right?
Different, yes.
Uh, but if you think that W hat ML as a as a uh, random variable, then you will get some distribution of the W hat ML, correct? Right? And our hope is that the W hat ML, right, should be the unbiased estimator of W. We are saying that it, or let us say I'm saying to you is that it is an unbiased estimator of W. What does that mean again? So what I'm saying, trying to say is this is my W hat ML. So this is a distribution of W hat ML, correct? So if you take different samples of X, right, these data points, you will get different W hat ML. And let's just say if I plotted that distribution of that, it might look like this. What is this quantity suggest to me?
Mean.
Expected value of W hat ML, right?
Yeah.
Correct. And when I say this W hat ML, which we have calculated, is an unbiased estimator of W, what is the other way of saying about this? Unbiasedness is when the expected value of the estimator, or this is going to be 0, or I can say in other words, it should be equal to W, right? True W, fine. It's okay if you are understanding, it's fine. Otherwise, no, not an issue. You should understand that this W at ML is the unbiased estimator of W. That means if I try to plot a distribution, right, for this W at ML, uh, the expected value of that distribution should be equal to my true W, and that is actually correct. Now, I hope you have remembered some things about risk and variance, right? So risk is equals to bias plus variance, or bias square, right? Bias square, I think it is plus variance. That is what it is. What is the risk of an estimator? Risk of an estimator is expected value of uh, w hat ml minus w, let's say square. Okay, and bias is what? What do you mean by bias? It is expected value of w hat ml minus w, right? This is going to be square of it plus what is the variance? Expected value of okay. I think there is some confusion in here. Okay, what is the variance of any? Okay, I think okay. Yes, sorry. I think here it is not like this. It is
Expectations of the data points
hmm?
square. The square of the data points with a random variable.
You know the deviation, right? You know the deviation of a random variable. If you have x as a random variable, what is the deviation? X minus x bar, right? So the variance is actually the expectation of expectation of
X, the variance x minus x bar into y minus y bar.
mm, not that variance. Okay.
Yes.
Okay.
Expectations of the a square into a square of the expectations. You go inside WML minus W square,
Hmm.
WML minus W square, minus W. A square of this, yeah, expectations of a square.
Correct,
A
right?
square, a square of the expectations plus expectations of the square is the variance. Am I right?
Square of the expectation and
Here, a square
uh
of the
yeah,
expectation.
okay, that is okay. It was like this you are saying, right? Expectation of
Yeah. I remember this one.
x square. Okay, but
Yeah.
previous step was what? Like I think it was this, right? X bar square, I think.
X minus x
And,
bar square.
like that. And then you just I think open it up and it will happen. Okay, okay.
Yeah.
I think it's anyway. It's not the part of the syllabus. I'm just
Hmm.
giving
No,
you
no,
the
just
quantity.
yeah.
Okay, will those who have not done this, maybe we can discuss it at any other point. But fine. What I'm trying to say is, if this is this quantity, right? Let us say this. Okay, I'll just put it down here as it is.
What we want to do here exactly?
Yeah, I will tell you what do you want to do. So this quantity, right? In this case, if you use this mlhat estimator, uh, this the expectation of, let's say, because this is going to be zero, right? Is going to be zero. This variance will become the risk right now because it's an unbiased estimator.
This will become zero if this one is W.
Unbiased. We said no, it is unbiased estimator anyway.
Yeah, unbiased. Yeah, unbiased.
Correct, right? So, oh, I think maybe I'll just put it down properly. This has to be like this. Sorry, this bias term is what? Bias term is to expectation of w hat ml minus w. This is bias, and we are taking it square and you are adding it. But when w at ml, I said it's a unbiased estimator, then this quantity will become zero. So this risk will become equal to the variance, and that variance, right, that is equal to this quantity. So w hat ml minus w, if I take it in terms of the let's say it's a vector, right? Anyway, w hat ml is a vector because w also is a vector, and if I take the square of it, that will be variance. And actually in this case it's a risk as well, that is equal to sigma square into trace of a matrix x6 transpose inverse. So what is this quantity here? So this is standard deviation here, right, of this distribution. Correct? Is that correct?
Yes, sir.
Right. So there is a w hat ml is a random variable, let's say, and you plot a distribution of about it. So uh, okay, one more part I wanted to tell you is that, let us say you have a w hat ml distribution like this, and you have, with, let's say, expected value of w hat ml which is equal to w, or leave about W. So this is your distribution, and let's say you have another distribution like this, which is the better one. The let's say this is one and this is two. This is
Who is
better.
better?
Two is
Who is
better. Why two is better? The
because
variance is,
variance
yeah,
variance
variance
is
is less, right? So
less.
whenever you find out, let's say if I take a sample and if I find out its estimator based on that sample, and if you take a sample and you find it out its estimator, it is very likely now that our estimators, right, both of our estimator will be very exact or nearly equal to the true estimator, right? True value of the estimator. That is correct.
Yeah.
Or not true value of the estimator, true value of the W in this case, right? So what you want is we wanted a lesser variance, correct?
Hmm.
So now I am saying that this variance is dependent on two quantities, which is sigma square and the trace of this matrix X6 transpose inverse matrix, right? Now sigma square is what? It is actually,
Variance
yeah, variance of the error, right?
error.
Yeah, that noise. Uh, so we are saying we cannot change it because we are saying that it is naturally occurring because it is of due to the nature or due to the human errors, whatever it is. So the only way to reduce this quantity, right? That means the gap between the true estimator, sorry, W hat or the estimator of W and the true W. If you wanted to reduce that variance, uh, we need to reduce this quantity, right? If I,
Trace of the matrix.
yeah, because we cannot do anything with this case, we'll have to reduce this part, trace of this matrix. Fine, that's okay.
Hmm.
Okay, what is this trace of the matrix, right? So trace of the matrix is basically equal to, okay, trace of, let's say, X6 transpose should be equal to what? The sum of
Some of the diagonal elements.
eigenvalues. Yeah, that is true. And
Eigen. Yeah, eigen value.
equal to sum of eigenvalues of X6 transpose matrix, right?
Hmm.
Suppose lambda 1, lambda 2, and lambda n, right? Because, okay, what is X is, X is what? How, what kind of matrix is n cross d or d cross n? D cross n.
Decrossing.
Yes, yeah, right. D cross n. So X6 transpose will be
D cross D.
D cross D, right? X6 transpose will be D cross D. So you have D eigenvalues, correct?
Yeah.
You will have this D eigenvalues. Now let's say lambda 1, lambda 2, lambda D are the eigenvalues of X6 transpose matrix. Sorry, X6 transpose matrix. Then what are the eigenvalues of this matrix? Inverse matrix.
Same.
No,
1 by lambda.
upon lambda.
1 by lambda 1. Inverse of the
Correct, right?
matrix.
Is it fine?
Yeah.
So then what will be the trace of X6 transpose inverse matrix? It is
1 by
Summation
lambda
of values.
sigma
to 1 to D
D.
upon lambda I. Is that
1
fine?
by lambda. Yeah.
So let us say, okay, I wanted to reduce this quantity, right? Stress of the matrix, so that I will be able to reduce the variance, right?
Yeah.
Okay. Now,
Mhm.
if my data set is fixed, if X is fixed, right? Can I change anything about this lambda I and lambda 2? No, right? So now we are saying that, let us say we are saying that expected value of W hat ML and W, right, is dependent on now sigma square and summation of I equal to 1 to D 1 upon lambda. Is it fine?
Yeah.
So to reduce the quantity, I should do something such that I should reduce this entire thing so that it will go down, right?
Mhm.
Right? Okay.
Yes.
So that is fine. Now that means I need some other estimator than W hat ML, right? I don't need this estimator. Suppose the new estimator is like this: W hat new is like this, x6 transpose plus lambda I. I introduced some other uh, value of lambda. Lambda is not the eigenvalue, right? Lambda is some other constant, fine, which is greater than 0. Is that okay?
Yeah.
Now I'm saying that this is the
This
new
is W new. This is W new.
yeah. So W hat F symmetry is like this, right? X is transpose inverse xy. Now W hat in new is this one. Okay, I have said that this is another estimator to me, and if I try to find out uh, trace of this matrix now, that will be what? It's going to be. What do you think about this? So how does it will look like? Uh, at each of the diagonal elements, lambda is going to be added, right?
Yeah.
So XX transpose, let's say the eigenvalues of XX transpose are lambda 1, lambda 2, up to lambda d. Now I'm saying that the what are the eigenvalues of XX transpose plus lambda I? Those will be lambda 1 plus lambda, lambda 2 plus lambda, until lambda d plus lambda. All of you agree with this part? Hmm?
Yeah. Lambda 1 plus lambda lambda. Yeah. Only. Yeah.
Right. So
Lambda will be added, no?
yeah. So let's say these
Lambda
are
is not the eigenvalue of this because only constant is that. No? Constant will
fine.
be added.
Okay. Suppose I'll do one thing. I'll just do with a small example here. So let's say you have this kind of matrix, diagonal matrix. So I'm just keeping it diagonal so that we can say that all the eigenvalues are the same as that of right, all the diagonal entries. So if I add some lambda and this matrix, the new matrix will be what? It is 1 plus lambda 0 0 0 0 plus or
2
2 plus
plus
lambda
lambda.
0 and 0 0 3 plus lambda. So what are the eigenvalues of this matrix? 1 2 and 3. What are the eigenvalues of this
1
matrix?
plus lambda, 2 plus lambda, 3 plus lambda.
Like that. So let's say lambda 1 lambda 2 to lambda d are the eigenvalues of xx transpose. Then the eigenvalues of xx transpose plus
Lambda.
lambda I, they are the addition of all of this, right? Lambda,
Hmm.
so all lambdas I have added into all,
Hmm.
right? Then what will be the eigenvalues of this matrix? This will be 1 upon lambda 1 plus lambda, 1 upon lambda 2 plus lambda, like that, 1 upon lambda d plus lambda, right? Fine. Then if I wanted to find the trace of this inverse, that will be equal to summation
Summation.
of I equal to 1 to d 1 upon lambda I plus lambda. Is that fine?
Yeah.
Hmm? Okay. So now if I wanted to see that whether it will change my variance or not, right? Correct? Hmm? So
Hmm.
is it fine till now? If you have doubts, let me know. Otherwise, we can move forward.
Purpose of getting this trace, why we are doing this?
Why we are doing this is because we said, right, this distribution, this w hat ml and w, the squared error of this, right, this
We
is
want
called
to
as the
minimize it.
yeah, mean squared error between w hat ml and w. right? We wanted to reduce this quantity, right?
Yeah. For reducing, we want to use the trace because only trace is required to be reduced, right?
Right.
It
Because
means
we
this
cannot.
is this is the objective function we are getting, right? To
Correct.
reduce.
Right. Correct.
Okay.
This
Okay.
okay for this fine, right? I guess that there is no problem with that. Hmm?
And the lecture, some different way it has been done, right?
No, it is not explicitly written like this.
Okay, not like that I'm asking. Okay.
Sir has
This
written
is now this is the objective function for us, right?
objective.
Sigma
Hmm?
for minimizing, right?
Not objective function. No. We don't wanted to do that. I'm just saying that now. Let's say my w hat ml. Okay, I'll just write down the comparison for you here.
Yeah.
So w hat ml is what? That is x6 transpose inverse xy, right?
Hmm.
W hat nu is, it is x6 transpose plus lambda I
Lambda I
inverse xy. Fine.
inverse x values.
We said that the expectation of this w hat
WML
minus
minus
w is
W
called as the
mu.
mean squared error between uh, that is this mean squared error is different from the mean squared
Yeah.
error loss we have seen earlier, right?
Mhm.
This is the error between true w and the estimated w by using the maximum likelihood. So, right, this looks like the squared error, right? The squared error between w hat ml, that is the estimated w hat or estimated w and w. And since we are taking its expectation, it is called as a mean squared error. We said that it is dependent on sigma square and the trace of x6 transpose, right? Now, and the trace of x6 transpose was equal to summation of I equal to 1 to d 1 upon lambda I, hmm? Where each of lambda is the eigenvalues of this x6 transpose matrix. Here, what I'm trying to say is expectation between this w hat nu and the w, that is now equal to sigma square summation of I equal to 1 to d 1 upon lambda I plus lambda. And if this lambda is greater than 0, right, what will happen now? Will this quantity reduced, or will that be same as that of this? If lambda,
Reduced.
yeah, if lambda is greater than 0, it can be reduced, or it will be reduced than this, right? Okay, that is right. But now there is one term comes out. So what we are saying is, let's say this r or let's say these lambdas are any r. So if this lambda is negative, what will happen? This may increase, right? This may increase. Any issues in that? No, right? Okay, so the point of saying anything here, okay, it's fine if you don't understand this completely, that is not a problem. The point here is lambda can be any real value, right? For some lambda this quantity go up, and for some lambda this quantity goes lesser, right? So there is one theorem which is called as the existence theorem, that says that this lambda, there exists some lambda, okay, there exists some lambda, uh, for which what happens, for which the mean squared error, right? So let's say mean squared error uh, will be lesser, or you can say that there exists some w hat nu, that also is fine. It's saying same thing. So there exists some w hat nu, so you will get some other estimator for w hat nu, which will have the lesser mean squared error between the estimator and the true w than w at ml. How many of you understood this statement?
Estimator in the sense,
So these both are the estimators, right? This W hat ML and W hat nu is estimator. If you remember it from stats 2, uh, the estimators can be anything, right? So let's say I can say that estimator W1 be some constant, let's say 5, right? That also can be estimator. There is another estimator which we can find it out by using, let's say, method of moments, right? There is another estimator which we can find it out by using Bayesian estimation, right? So there is a Bayesian estimator, and there is one estimator which is a maximum likelihood estimator. So how will we decide that which of these estimators are better? Correct, right?
so we are saying that there is some W hat nu which is better than W hat ML.
Yeah, which will give me lesser mean squared error between. Yeah, you can say that there exists some W hat nu which gives me better or lesser mean squared error. What do you mean by mean squared error again? The error between the estimator and true W. Is that okay? Okay, I'll write it down for you. So there is this estimator. Let's say I have found it out by using a method of moments. Fine. W2 is the estimator which is I found out by MLE. W3 is by using, let's say, Bayesian estimator. Fine. Okay. Okay. Now what I'm trying to say is, uh, maybe expectation of W1 hat minus W, right? A square. That's a square is greater than, let's say, expectation of W2 hat. So okay, all of them are hats minus true W square is less than expectation of W3 hat, uh, or okay, I'll let this less than or equal to W3 hat minus W square. So what do you think, which one is better, or which will have the lesser mean squared error?
First one.
Third one,
W3.
3, right?
Oh, yes, yes.
So
Let.
yeah, right. So what we are trying to say is that there exists some W3 hat which will have the lesser mean square error. Fine. But this W3 depends on what? What quantity? It depends on this lambda, right?
Lambda.
So now you will have to find out that lambda. If that lambda is something else. So suppose, okay, I'll give you two examples. If lambda is greater than 0, will this quantity be lesser than this? Okay, let us try to compare here,
Yeah, it will be lesser.
right? If the lambda is greater, uh, will this quantity will be lesser, right?
Yeah.
Right. But let's say if the lambda is less than 0, what about this?
Error will go up.
Right, it is definite, right, in this case. Hmm? So the existence theorem says that you will find out such lambda that for that particular
What
lambda,
will happen when the lambda is negative?
if the lambda is negative, what will happen, you tell me, na? Suppose,
And then negative,
okay, if the lambda is
it will,
negative,
it will increase. Error will increase
how it will increase?
because the denominator will decrease.
Right. So denominator will decrease and this will go up,
Right
right?
now. Right now.
So
Same now.
yes, right. You're
Okay.
absolutely right.
Okay. Okay.
So that means for that this kind of lambda, I don't have lesser mean squared error, right, than the W at ML. Hmm? For this choice of lambda, do I have the lesser mean squared error than W at ML? Yes.
Pardon?
Yeah, yes, sir, we are having.
For this, we have higher MSE between W hat ML
Yeah.
and W, right?
Hmm.
Or higher, or
Greater.
yeah,
For greater lambda, we have lesser. Right.
correct, right? Fine.
Correct.
So I need to find out that kind of lambda. We don't, we have like the choice for that lambda through like
Is
you,
all with R, yeah.
yeah, you can actually get any real number there. So we need to find out that particular lambda, so that but see, it is not possible for every choice of lambda. It is only possible for the specific choice of lambda. That is what we try to say. Actually, I wanted to show you by risk and variance thing, but let us say for now we will not, because it will get like more complicated. But at least by this comparison, you will be able to understand that there exists some lambda which gives me lower mean squared error between the estimator and the true W, and that depends on what, this lambda. So and this lambda so the good lambda you can find it out by using the cross validation technique. Okay, cross validation technique. uh, Maybe can I skip this part, cross validation part? I think that's not like very difficult to understand, right? Is that okay? Cross validation, I think it's like you just take uh, uh, like 20-80%. If it is there, you total out of the total training data, you use 80% of the training data uh, for the
Training.
train, and 20% for the validation, right?
Yeah.
And there is one more term like k fold cross validation. In that, actually what you do is you divide, let's say if the k folds are the 5 folds, your entire data you divide it into 5 folds, right? Like 20-20%. So in the first cross, okay, what do you do is, let's say you divide it by, let's say 5, 1 2 3 4 and 5. So uh, in the first you use this as the validation set and the remaining as the training set, and you what do you do, you just note down the error. In the second case, you do this as the, or you make it this as a validation set and other thing as the training set, and you note down its error. So you how many errors will you be able to find it out here?
5.
Five set of errors, right? Training, like 5 training errors and 5 validation errors, you will get it, right? And now what you do is you choose uh, that set which will give you the least error. Fine. This is also very important concept actually. It's not it's there in the lectures in that detail, but I think that that's concept also is much important uh, with respect to your quiz. Okay. And there is one more thing is the there is one k fold, and then there is another validation technique is leave one out, right? So in that case, what you do is like out of the total samples, you will keep only one data as the validation set and the remaining as the training. So you do it like for, so you can say that as the n, if you have n examples, right? So I can say that as n minus 1 fold cross validation. Is that correct?
Yeah.
So k will be here n minus 1. So you divide the data into n minus 1 folds, and you do that. You find it out its validations and training errors, and you do the you pick that that uh, that lambda which gives you the least validation error, right? It does not mean that you should have that least training error. You should have the least validation error. You pick that lambda. Fine. Then there is one more concept. Okay, so we said that there exists some w hat nu, which is like this: x transpose plus lambda I inverse and xy. But see, this is there, but how do you find it out, right? How do you get that? So you get this estimator by using the Bayesian estimator. So basically, this is nothing but the Bayesian estimator. Fine, Bayesian estimator. In Bayesian estimator or in Bayesian modeling, what do you do generally? You in MLE you find out the likelihood of the data. In Bayesian estimator, what do you do? The posterior density, right? The posterior density, or let's say in this case, the likelihood, it is dependent on what? Likelihood and prior, right?
Into prior. Divided by
Yeah. So this prior will be the function of what? Or prior. Okay. prior is a function of leave about it. What will be the distribution of prior?
Same as the distribution of the first
Parameter, right? Not
parameter. Yeah,
same.
yeah,
Yeah, if it is
parameter.
same, then that prior is called as a conjugate prior, right? If it is normally distributed, right? Same is called a conjugate prior. That is different. What I'm trying to say is here is, so likely in the likely prior we have some information about the unknown parameter, right? Basically, our entire problem is to find out that W, or to estimate that W, right? In this case, in the maximum likelihood estimator case, we treat that W as a constant and you find out its likelihood. Fine. You are saying that there is a specific W. You don't consider that W will have some kind of distribution. In Bayesian modeling, you consider it as it is having some kind of a distribution, right? Fine. So likelihood you get it from this. Y given X will have some distribution as W transpose X and sigma,
Sigma
right?
square.
Right. And what about this? Prior will have the distribution of, it will also have some distribution, and it is, let us say it is, if I wanted a conjugate prior, I'll have this choice, sigma, oh sorry, 0 as a mean, and let's say gamma square I is the variance. Fine. And this prior is a prior. Okay, this is also in d dimensions. Okay, now you find it out. It's okay, the derivation is there. I will not do that derivation right now today. I think I in the previous session I think I have done it. So I'll just talk about what we gain through this, right? So we get after this Bayesian modeling, you get the uh, estimator for this, for W, that is exactly be equal to this x transpose plus 1 upon gamma square to I inverse xy. But this you get it when you have that sigma square, when you think of sigma square as 1. If you wanted that sigma square to be something else, then this will have some changes. You'll have to figure it out. uh, Fine. And how do you do that? You'll have to do that solution. Okay, you will have to equate that solution and you'll find it out. This is also again very important concept, how to find it out. If you have sigma square uh, which is not equal to 1, what will be the estimator? Have you found it out previously? Anyone has tried it out? This is again important one. Okay, do you want me to tell you something about it, like how do you do that? What will be the likelihood? Can I write it down? Likelihood I equals to 1 to n e to the power minus yi minus w transpose xi
Remove the full, okay.
square to sigma square.
Few sigma square.
But when you treat as sigma square as 1, it will become 2, right? And the prior will be what?
1 upon
1 to d e to the power minus w square upon 2 gamma square. Fine. Is that okay? Why it is like that? Hmm? Because y given x was distributed as this,
Zero.
normal w transpose x, and what is it, 1, and that gives me this density, right?
yes.
And this is coming from where? When w is distributed as normal 0 comma
Zero.
gamma square, gamma square.
Gamma square.
Is that okay? Hmm?
Gamma square is the variance of the level.
So if you do it, and okay, so now what will be the change here? It will become 2 sigma square. If it is not 1, there's 2 sigma square come in here, right? And then 1 upon root 2 pi sigma will be there, but anyway that is constant, and this is a proportionality sign, so we don't worry about that. 1 upon root 2 pi sigma. So this will become 1 upon this to the power minus yi minus w transpose x xi square upon 2 sigma square, and this will be, can you think about this? What is this part? If I take a product, it will become a sum right here. So it is like, let's say
It could take log then.
yeah, no, not logarithm, normally also. So what is e to the power minus 1, e to the power, what is, okay, e to the power minus 1, e to the power minus 2, e to the power, what is the product of this? It is e to the power 1 plus 2 plus 3, right?
Yeah.
So if it is like this, it will be sum. So product of all of this will be equal to what? It will be the e to the power minus
Sum of powers of
I
P.
equal to 1 to d w square, right? Or let's say, okay, it has to be I, let's say wi square upon 2 sigma square, right? And that's going to be length of the w vector. If you guys have forgotten this, right, you may struggle in the exam. I'll tell you, this is because this is important. You should know.
Week 6, no?
Huh?
Week
Yeah, yeah,
6, no?
yeah. This derivation is important. That's why I'm actually writing it down for you. So this is gamma square, right? Gamma square. Okay, is that fine? This is 2 sigma square. This is 2 gamma square. But this is a product of I equal to 1 to n, and this is now happen to be like this. So what is the map estimator from there? Is basically nothing but arg min of w, right? Hmm? Arg min of w, this is half summation of I equal to 1. So okay, this will happen after taking a log, right? So if I take a log of it, this will be half summation of I equal to 1 to n e to the power, not e, now e will not be there. What's going to be there? Yi minus w transpose xi square, and 2 sigma square here, correct?
Yeah.
Plus 1 upon 2
2 gamma square.
square. Is that fine? That minus minus sign, actually this will become the maximization problem, right? And that minus will go to the this. So this is what w hat map looks like when you have considered 2 gamma square, and when your gamma square equal to 1, then this will become this, right? Correct. So this is your with sigma square, sorry, not gamma square, sigma square. Without, when sigma square equal to 1, what is the solution to this problem? It is equal to
1 by 2.
this is what it is. Is that okay? So now we'll have to think, if sigma square is there, is if that one is not there, and if sigma square is there, what should be the w hat map will look like? This is very important. You just try it out.
When you differentiate it, then we get this, no? X transpose.
Yeah, basically you don't need to differentiate now. If you differentiate, you will get it. So you will have to differentiate this quantity, right? That's correct.
Yeah.
And you know,
Then we will get this, no?
definitely. But then that sigma square will be what? That you will have
Or
to
maximize this W map,
minimize.
right?
No, minimize is fine. You just differentiate it and equal to 0, you'll get it anyway.
Okay.
But try it out, okay? Just don't remove that from your mind.
We
So
forgot this one. We forgot
yeah,
this.
that's
We
what
did
you
it.
just, yeah, you just go through the lectures once more and you'll
Yeah,
do it.
it is required. We forgot this.
So this is what actually is a solution for a ridge regression. So that whatever the Bayesian estimator is giving to me is a solution for the linear regression. So this is called a regression, right? So I'll just talk about the qualitative side of it instead of I think whatever I have discussed it previously already discussed is there in the lecture. uh, if you remember it, where is okay qualitatively what are you trying to achieve using the ridge regression? What do you think? Hmm? We are finding out so what is the ridge regression will look like? It is arg min of, or let's say arg min of w, right? Rd, and your statement is what? Objective function is you're trying to minimize this, right? Y minus w transpose x square plus lambda, or let's say 1 by 2, 1 by 2 is there anyway. 1 by 2 we don't care about it. Is that okay? Is that fine?
Yeah.
I hope all of you are remembering this. This is a regularization parameter. Correct, right?
Regularization.
And this regularization will be if I have this prior of w as uh, normally distributed with 0 gamma square and or gamma square I, and your y given x, the labels are distributed with respect to w transpose x and 1. What is this regularization parameter lambda is? That is exactly equal to 1 upon gamma square, right? Hmm? To think about it, what is the solution for w star or w hat ml? That is xx transpose pseudo inverse xy, right? And we said that w hat nu should be something which gives me this quantity lambda I inverse xy. This lambda is basically equal to this, right? And this lambda is called as the regularization parameter. Okay, are you guys here or you left it already? Okay, all of you are here.
No, no.
Why I'm discussing this is because these are all important with respect to your exam, the coming exam. The questions are not like most of the questions are not related to uh, like problematic. Like problems are not there. It's like upon they are based on your understanding of the course. So you don't need to solve the equations or numericals. You need to understand it. If you understand it, you'll be able to solve that paper. Are you able to connect all of this? The regularization parameter, the new hat ML.
Numericals based on this, it will not be there,
No,
right?
no,
Question.
no, no. All are like qualitative. So okay, I will just summarize it once more. What is W hat ML? That is equal to W star, which is XX transpose inverse
XY.
XY. W new hat. What we said is XX transpose plus lambda I
Lambda
inverse
I.
XY. And why we
Inverse
wanted
XY.
this W hat new? Because it is reducing my
Error.
mean square
Error.
error between
Error.
what? But the error between not the labels and the perimeter value.
Okay.
It
Let
is
Error between parameters.
error between the estimate and the true parameter, right? Is that correct? Correct?
Which one is true? W star is true, no?
No,
W is
W
true.
star also is not true. W star also.
W and W.
Sir,
This
that
is
is pseudo inverse, no, sir? W hat ML.
yes, pseudo inverse. Just okay. Right now, think about inverse. We are just ignoring that case. That's fine. You are correct. It should be pseudo inverse, and again, this also has to be pseudo inverse.
Okay.
But for comparison, why we wanted this part? Because I'll get some w or I'll get some lambda, which will minimize this quantity, right?
Yeah.
And that is
Okay.
actually we have achieved using the regression. This is same as that of regression thing. X is transpose plus lambda I inverse xy. So this new thing is nothing but a regular or this parameter by using ridge. Fine. Is that okay?
Okay.
And
Yeah.
and in this case, we are calling this as regularization parameter. Hmm? Fine.
Yeah, yeah.
Hmm? Hmm. Okay, good. So, but this lambda is coming to be equal to what? 1 upon
Gamma square.
gamma square. So this lambda actually we are getting from the uh, once, or I'll say that from the Bayesian modeling, right? This W is nothing but a Bayesian estimate, right? This is ML estimator, this is Bayesian estimator. But this ridge regression will, okay, will that be always true that it will be the error, this mean squared error between, let's say, okay, is it guaranteed to me always that,
For a better choice of lambda, it will be better.
yeah, but is it always guaranteed that this is possible always? W ridge W square. Is it always possible? This relation? Not always, but there exists some lambda which will give me that, right?
Yeah.
Okay. And if that, okay, this is fine, right? This is fine?
Yeah.
Okay. So I'll leave that right now here. Uh, and we, okay, what are the solutions?
In the reach, it will be lesser. The error will be lesser, right?
This error uh, will be lesser, yeah, you can say that, but it is not for always that lambda has to be very specific, right? And if
Yeah.
that lambda,
Then, if it is a regulation
yes, yes,
parameter, then it will be lesser,
yes,
right?
yes. But now, what this is a solution of which problem? Arg mean W y minus W transpose X square, right? Is that okay?
Mm.
This W star is a solution of to this problem, right?
Yes, yes.
And this W range is a solution of which problem? A lambda, right? This will regularize what? Uh, okay, so this is an unconstrained optimization problem, right?
Yeah.
What about this? This is also an unconstrained one, but can we make it into the constraint problem? We can make in this case, and that constraint problem will be like this. It will be minimize that W in RD square such that uh, this W square, right, will be less than equal to some theta. Fine. These are the both. These both are the same things. And if you think about only this, right, the only first part, it will actually gives me the solution of what? This one, WRTML, right? If I only solve this problem, this is WRTML gives me. If I solve this problem, this will give me rich. Okay, fine. So if I try to, let's say, W1 and W2, or okay, this is W1 and this is W2. So I'm supposing that your data is in 2 dimensions, and if your data is in 2 dimensions, you will have uh, two parameters, two W1 and W2, right? These two parameters will be there. Is that correct?
Yes, sir.
Okay. So okay, if this is fine, then can you? Okay, let's say this is W hat ML, right? This is solution. Let's say this is a true solution of W hat ML. Fine. What does it will give me? W hat ML guarantees me what? It guarantees me that this quantity W transpose X is
Minimum.
minimum. This is a squared error loss, right? So this quantity squared error is a minimum at W hat ml. Fine. What about ridge regression? So ridge solution actually exists. So this is what W hat. Okay, what if W is a vector of two quantities, W1 and W2, right? Length of W will be what? Or length of the W square is what?
W1 square plus W2 square.
So can I say that it is a equation of a, so okay, and then and what we are saying, okay, let's say W1 square plus W2 square is less than or equal to some theta, right? Less than or equal to some theta, right? And that theta actually is a function of lambda, that is okay. But this is kind of looking like a equation of a circle, correct? With radius,
0.
not zero,
No,
Theta.
no, 0. No,
root of
theta.
theta, root of theta,
Root of
basically.
root of theta, yes.
Right, so it is a circle,
Center at origin.
center at 0, right? So because, right, okay. So now each of the vector inside is, right, this vector, this one vector, this another vector, this another vector, or maybe you can say this vector, all vector will satisfy this constraint, right? Correct. So entire space within this circle will satisfy this constraint, right? Hmm? Fine. If you are okay with this part, then I am okay. Then we can go
Yes,
forward.
sir.
Fine, right?
Yes, sir.
Okay. So, but what about the functional value of W? So, what are the f of W in case of ML estimator or the squared error? When we consider that noise as a squared error noise, in that case, f of W was y minus W transpose X square, right? Basically, right? And we are adding some constant here in case of the regression. Is that correct? So can I say it is f of W hat ml? This is f of W hat ml plus if you add something here. So this is some constant, right? Length times some W is some constant, right? This is my f of W. This is my new f of W. Is it correct? Hmm? Is that fine?
Yes.
So, or let us say it is rich, WR. Okay, WR is like this. So this function will be also be like this, na? Y minus WR transpose X square, right? That is equal to this quantity Y minus, let's say W hat ml transpose X square plus some constant, right? And it is a positive constant, right? Hmm? Hmm. Right, na?
Yes.
Okay, so we know that the the squared error loss. So from here, what we can conclude is the squared error loss uh, for W hat ml is always less than reach, right? Just give me a minute.
Sir.
Sir will be back.
Is that fine? This is fine. No issue
Yes,
still
sir.
there, right?
How many topics are left?
Yeah, two only. I'll just make it quick. Huh? Maybe give me
Okay.
5 minutes. We'll cut down over there. Maybe I think one discussion is remained, but that maybe if you want, I'll just post it on the discourse later on. That kernel regression related one. Fine?
Okay.
Yeah. So here, if I try to, okay, I think the other things you can just consider later. Let us say here my w hat ml is there. Where will my solution of w reach will lie? It will be somewhere here, right? And it depends on it depends on that constraint. So okay, I think okay, maybe you can check the lectures later on. This quantity, right? W minus w hat ml, it will actually follow an ellipse. So and w also is not going to be a true w, right? It's an estimator for w. And if you think about this, right, if you, it will be like ellipsoid thing, and it will cut somewhere here. This ellipse where it will cut to this w square less than theta, right? That circle, that is the solution for wr ridge 1. Now the question here is what, why we see, one thing is for sure, right? If I have w hat ml solution, that will give me what, minimum square error, right? Is that okay?
Yes.
W hat ml gives me the minimum squared error, error loss. Fine, that is the loss between y and w transpose x, true label and estimated one. W reach is not the it will not give the minimum, right, than w hat ml. But why we go for w reach than the w hat ml? So we already have seen that what will happen if I choose the ridge regression is, we have seen that, right? Ridge regression solution comes from the Bayesian modeling, and we have seen that from our parameter estimation techniques, that this actually gives me better this part, right? Lesser mean squared error. Is that fine? Is that okay? It does not give me the minimum squared error, but it will actually gives me the, so the whatever the solution I'm getting, right, that might be like much closer to the uh, exact w, you can say like this, right? So or it will reduce the variance in that distribution of w. That is the part here. So what does regression do is, it will, okay, this is what this is what different perspective I've given to you. You may just watch it later and you can just find it out, that is correct or not. Fine. So okay, what we are trying to achieve here, one thing we can notice, again I'll just write it down, solution for both. Suppose this is my solution is w r, this is w r hat, and suppose my w hat ml is somewhere here, w hat ml is somewhere here. So this is w2 and this is w2 and w1, and this is what, sorry, w hat ml means what, it's again a data point, right, in this space, w hat w space, right? This is my w hat ml, right? So what we are able to achieve here, or what you can see by looking at these two, the length of w hat ml, what is the what do you think about it? Which length is greater?
Large. ML is large.
ML is large and ridge is lesser, right? So that and both of these w's are actually what, they are like of these two, right? W1 and they are in the into that space, right? W1 and W2 space, correct? So when this will happen, that W R is lesser than W at ML, that means these two quantities, right? They are lesser, correct? Is that correct?
Okay, sir.
And
Yes.
right, and this circle, whatever I have written, it depends on what. So basically, this is depends on this theta, right? And this theta is dependent on the regularization parameter. So if my regularization parameter is higher, like much higher, what will happen then? The size will get reduced, right? The circle size will get reduced. Is that fine? And your W rich solution will also, or the that vector, right? It is getting lesser and lesser. But it will not push to the zero. Fine. It will not push to zero. Is that correct, right? It will be somewhere there, because when that will go to 0, when you have the 0 radius, right? But that is not going to be possible. Is that fine?
Yes, sir.
I hope you are understanding what is the difference. So, but see again, let us say you have the features, and why this W1 and W2 is very important, because the prediction which we are doing, right, it depends on this, right? What is the prediction? So y1 hat is the prediction of W1 x1 plus W2 x2, right? Like that, right?
Yeah.
Correct. So suppose your x2 is, let's say, 2 times x1. What is that? It is a dependent feature, if it is there, right? So do I have to give some weightage to this x2? Do I need x2 again? Okay, let's say
No, no.
no, right? if
Don't
if,
need.
if I have only w1, I'll be okay with that part, right?
Mm.
Correct. So, or but ridge regression, what does it do is, it will force this w2 to go lesser, but it will not make it 0. Fine. Correct.
Yeah.
So that means if you have this kind of linear dependency between the features, right? This is a dependency, right? Linear dependence, or okay,
Yeah.
you have any kind of dependency into the features, or sometimes if the features, the feature values are 0 for most of the examples, these features are called as sparse features. Maybe you will learn about that also in some other course. But in that case, you might not want this w2, right? What this range regression solution is guaranteed me to have these weights, right? These weights w1 and w2 to be small, correct, right? But it is not guaranteeing me to have the have it as 0. So there it comes, the lasso regression, right? And lasso is basically what, uh, that is what this problem is, like this: w is rd, w in rd, and this is summation of I equal to 1 to n. And this is same, right? This is same as that of y minus w transpose xi square, or yeah, like whatever, like if you can w transpose xi minus y also is fine, plus lambda. So it will take a L1 norm. Fine. Okay, I'll write down all this. WR is minimizing W over RD, summation of I equals to 1 to n, yi minus W transpose xi square plus lambda W square, right? And the third is what? Your WML solution. And that is minimizing over W, which is in RD. This will be summation of I equals to 1 to n, yi minus W transpose xi square, right? This is this solution, right? W hat ML. Uh, this will give me the minimum squared error, right? Between features and the label. Is that correct?
Yes,
This does not. This does not. But what they will give me, they will force my W's such that any dependency between the features, right, that has to be reduced. So basically they are based on this popular term, I think all of you must have heard it. It's called as a bias variance trade-off, right? So w hat ml actually will have higher variance, right, but a lower bias. So what you do is you just try to reduce that variance, and one of the techniques we have used to reduce the variance was this one, right? The ridge one. That's how you find it out, that w new hat. And this is the ridge technique, that is the solution actually lies on the intersection of this ellipse and this circle, right? That ellipse is, and uh, there is this lasso which is absolute, which takes the absolute values, that actually, if you, okay, you understand it, right? Like it is w1, uh, absolute value of w1 plus absolute value of w2 should be less than or equal to theta, right? And that gives me this this graph. If you remember it from maybe I don't know, we have studied it stats or maths somewhere, you might have studied it. So this is W hat ML. Wherever this ellipse, right, which is coming out from here, it touches this part, that is your rich solution, and this ellipse, right, it will touch one of the corner points, and that will give me the lasso solution. So in lasso solution, what happens is you
One of the feature will be forced to zero.
yeah, one of the features, but one of the features when we are saying is like in this case we are actually looking at only to the two features, not features actually, we can say the one of the weights, right, corresponding to that features, because your prediction
Parameter.
prediction was dependent on this, right, w1 x1 and w2 x2. So if this feature goes sorry, this weight goes to 0, automatically the influence of that x2 over prediction of, like for the prediction of y, right, it will anyway go off, right, it will become 0. Are you understanding the point now?
Sir, it can be more than one also, no, sir?
Yeah, yes, this is like for visualization purpose. In general, what happens is you have many features, x1 x2 to xn features, right, and you have corresponding w1 w2 to w1. So visualizing this w1 to wn space, we cannot draw it, right, we can draw only two. So this prediction actually was dependent on what, let's say w1 x1. So first label is the linear combination of this, right? wn xn. So lasso will give me that more than one weights, right, or maybe one weight also, or more than one weights will become 0,
Okay, sir. Okay.
and that will happen. Let's say w2 and wn are getting 0, so this will become this quantity, and this quantity will become 0. So whenever I am predicting this y hat, right, I'm not what is it, like I'm not considering this x2 and xn into account, right? Is that fine? Have you heard the term of overfitting?
Yes, sir. Yes, sir.
So what do you have, what will happen in overfitting?
Kind of some error, like
So
Training error will be less and
yeah,
test
what you
error
Yeah.
will be high.
Training.
correct.
Test error is more.
Yeah, but why it will happen is it, so your model actually tries to uh, you know uh, tries to go through every data point, right, every data point,
Yeah, right. Yeah, right.
right.
Sir.
So and that is why during training you will have that lesser error. So here if you think about it, it's w hat ml actually gives me the minimum error, right, because it is considering all the features, right, even if they are redundant, correct. We are not forcing any of the weight to go to 0. That means we are using every feature to predict y, or to get that y hat, right, that model, correct. So it's kind of overfitting here in this case. WR and or the rich solution and the lasso solution actually making it uh, less overfit. But it's fine. Okay, if you don't understand it this point, it's fine. Maybe we'll discuss it at some other point. But I think all of this is understandable, right? Where the solution lies and what are the meaning of it.
Yes, sir.
Fine. So I think we'll stop it here. One more thing is remained from my side is that the discussion we have stopped in between, but it's kind of very late right now. Maybe I'll make a discourse post for this, uh, and if I get like if I get time, right, maybe we can have like session for 1 hour if required. But if it is not, first of all I'll write down that solution onto the discourse, like what is the meaning between that f1 and like that alpha and okay, what is the relation between alpha and w, right? So I'll write it down. If you understand it, it's better.
Yeah, on the discourse, right?
I'll
Properly. We will do it.
sure.
Already
You
we have done that, but
yeah, I
the
think
pending part is.
one of the sessions I have done that, but I just not able to recollect it today.
Hmm.
So do one thing. You can also
It is. I think it is a conversion of the data points into the feature
see
vector.
W
Right.
actually
Huh?
is W actually is a combination of data points, right? So that alpha
Yeah.
W star equal to X alpha star.
But alpha is the combination of the feature vectors, right?
Yes. So that
Am I right, no?
yeah. So right now I'll not maybe comment on it.
Okay,
I'll
okay,
finalize
okay.
it. So that's
You
a
know,
part.
I have learned through your class only, and it's somewhere it is in the
I think
video
one of
also.
the sessions. Yeah, I think one of the
Yeah,
sessions.
you have clearly explained it properly,
Yeah,
but we also missing because the pressure of the quiz too,
no,
because
fine,
we are
fine.
not able to.
No issue.
So please do that also, and
Yeah, I'll
because
put on the
this week 6 we have not gone through properly, so we could not capable. I will do it this week
Sure,
again,
sure.
okay?
Okay, and
Because
you go.
last
One
time
more
also
thing is,
we,
all of you go through this, derivations part, right? At least try to understand what is it exactly. I have tried,
derivation of this lasso, no?
not lasso. Lasso is not required. At least
Which one? Which
that
one?
ridge, right? Like how that ridge solution occurred. That W hat new and all. I just
Ridge
mentioned.
I will go through, but I have not gone through there because it is untouched. Okay.
Fine,
I
fine.
could
But
not
that
do
is
that in
important.
the last time also. Yeah,
Uh,
I will do that.
don't
Got it.
skip that part, okay? That entire week 6, don't skip it, because like there are few questions from week
No,
6.
we could not do that because the week 5 was also included in that. No? So
Week 5 is easier. Week 5 is easier comparatively to
week
week
5 is easier.
yeah.
Week 5 and week 8 is easier. Week 6 is something, yeah.
Yeah, I think week 7 also is fine. Week 7 also is like not
Yeah, week 7 is also fine. Week 6 is
Oh,
typical.
yeah.
Okay, we'll do
Okay,
it.
okay, okay. All the best for all of you. Okay. Uh,
If you have some
what?
good videos of week 6, na sir, just post it on the Discord.
Sure,
We
sure.
will
Yeah,
go through them
yeah.
because a number of things are that we don't have time to
Yeah,
go
do
through.
one thing. No, just go through the lectures once for week 6.
Okay,
Hmm?
sure,
Otherwise,
we will go through the lecture, sure,
yeah,
but after that, one video is required so that we get it clear. Okay,
fine. Okay, okay.
okay. Please do it until tomorrow. We will go
Yes, yes, yes. By
because
tomorrow, yeah,
this part is untouched. I know that.
yeah.
Okay,
No, no. By tomorrow, I'll post it on the discourse. Fine.
okay. Thank you,
I'll
thank you.
make clear
It's too late today. Okay.
between W and X alpha, and I'll try to, let's say, if I can, if I possible, if I'll try to visualize it in both the ways.
And one revision system more will be there, no?
Yeah, it is there, but that will be for week 7 and 8. I think that will
7 and 8. Okay, okay.
Friday.
You just, yeah. You
Yeah, but
just,
yeah, still it will have 2 days of time. So I think you should
yeah,
prepare for 5 and 6, uh, or if you have time, you can go through 7 also before that.
yeah. We'll go through.
Yeah, depends on like how many subjects you are taking this term. It depends on that as well. I don't know.
Yeah, that's why now because the number of things are there, we have to do that also. Okay,
Thank,
okay.
yeah, thank you. Bye bye. Good night.
Okay. Have a good night. Good night, everybody.
Thank you, sir. Good night, sir.